right. Welcome to Jupiter Brain, everybody. My name is Josh. This is
Albert.
And today we have a very special guest, Jack Woodward, our first student guest. I'm super excited about. We're going to be talking about quantum mechanics. We're going to be talking about probably a little bit of student life.
Modern physics.
I would kind of love to know where you're from and things like that.
Sure.
But yeah, so here at Jupiter Brain, we like to say that we are...
engineers by day
and philosophers by night.
Okay, cool. I like that.
Yeah, because you have to think deeply about all these different things that we're learning.
Yeah.
And like we were talking about before, right? It's like, I don't want to say there's not enough deep thinking, but I feel like we could have a little bit more, right?
Yep.
Yeah.
And I feel like we got to find ways to or figure out how to make that more prevalent.
Spark the joy of learning, just spread the conversations.
Yeah.
Yes. But anyway, so yeah, I'm super excited to get into this, so let's just get into it, right?
Sure.
So me and Albert, we like to start every podcast with sort of like how our week went, right?
Okay.
And so, how'd your week go?
My week was good.
Or in this case, you can talk about how the last 2 weeks go, because break.
Yeah, what did you do under the break?
What did I do over the break? I went to Lubbock to go visit my brother. That's where I'm from.
Okay.
I grew up in Lubbock, Texas. I lived there for the majority of my life. I was born in Stillwater.
Okay,
so,
Stilly.
Yeah, my dad was getting his degree.
You're not a Cowboys fan, are you?
Oh, well, I can't help but be a Cowboys fan. I think I always will be.
Boomer.
I know. Yeah, I was gonna go to OU for a while. I planned on it, and being the black sheep of the family, I was gonna be, but yeah, I decided to stay here at UCO, and I just love it here too much, bro.
Okay, nice. Yeah. And so you're an electrical engineer, right?
Yes. Yeah.
And so what year are you in?
I'm a junior. Yeah.
Okay.
So 3 of my classes this semester, like if you were to look at the flow sheet, like the flow chart, 3 of them are on the first semester junior portion, and then electrical science is the only one I think that's on the second semester sophomore.
Okay.
So
Cool.
Yeah.
Cool. So yeah, how was your break? How was
it? It was good, bro. It was good.
Did you go and do anything, or?
I mean, really, I went to Lubbock, and me and my brother, bro, we just watched football and sat on the couch. He just bought a new house, so it was cool he's finally like getting settled in, like got a couch and stuff. So it was nice to just go and spend some time with him, and then this past week really academically these past 2 weeks have been nothing but electrical science. Like that course, man, has just been like
Dr. Abubed.
Dude, Abubed, he don't mess around, bro. Yeah, he doesn't mess around, and we had a test yesterday, which it went good. I mean, like Abubed's exams, like half of them are multiple choice. They used to be full, like completely multiple choice. I heard. Was it like that when you took electrical science too?
Yeah, it was fully multiple choice.
Yeah, and then the other half was he changed it to where it's like partial credit, like you show your work and stuff. So I passed the multiple choice part, which I was very happy about.
He gives points for working that. What?
Yeah, I know.
See, I missed that. I barely passed that.
Because there's a second section now where you could do your working. It's like the what do you call it?
Partial credit.
Partial credit,
yeah. I mean, I think what's hard about those tests, right? You think, multiple choice, this is gonna be, I got this in the bag.
Nope.
Yeah. Because there's typically 5 answer. There's 5.
Yeah. A, B, C, D, E.
Yeah. Exactly. And that it can be a little, I don't know. You feel like you have too many choices, right? Yep. And so the thing is what's interesting about Dr. Abubed's test, right, is that you have so many questions, right? And so you're not really able to work all of them out. There are some which I think he it intentionally does is like some of the questions will be able to solve intuitively if you have that intuition, right? And you can just sort of look at the problem like, okay, well, if that's and come up with an approximation, right? And then hopefully one of the answers matches your approximation. But I think that's what's sort of tough about his electrical engineering course, which everybody sort of knows, like that's one of those make or break classes.
It is. It is, and honestly, like when I took the first exam, and it was all multiple choice, and we also had a partial credit too. I was kind of like a little upset that that's how this course was going to go, because every problem is, I mean, each problem takes you 10 minutes. I mean, really, 10 or 15 minutes. And so, and it's all math and it's all steps. And I figured, it'll be like, you know, electrical science is going to be like my previous courses where I get to show the professor, hey, you know, here's my equation. Here's me breaking it down, making substitutions. Maybe I missed a negative sign, -1, you know, -2. Yeah. I get my answer wrong by a tenth or, you know, whatever.
It's like in mathematical physics, right?
Yeah. I mean, yeah, right. Like, you know, each part it's compartmentalized and it's all, you know, and they look at it as a whole and then look at each part and kind of grade you, you know, partially. And so, I don't know. At first I was really upset about it, but now that I feel like I've done more nodal analysis and mesh and like just looking at circuits, I do kind of see like, you know, you either get the answer right or you get it wrong. Like there is one answer to the amount of power that this, you know, resistor is absorbing. Yeah. And so he's just, I can kind of relate to him, you know, and it was really cool. Like, you know, he comes off as this like real, you know, like rough edged dude who, you know, cuts no slack and is like just Mr. Serious all the time. Yeah. And our test that was yesterday was supposed to be Tuesday of last week, and I went to his office hours, and I had a question on Monday, the day before, you know, I thought our test was going to be, and I went in to ask a question, and, you know, he was like, "What's up?" And I was asking him about this problem on the practice set that he gave us, and he just kind of stopped me, and he looked at me, he was like, you know, he was like, "How about I just change the test to next Thursday?" After the break. And I kind of looked around, I was like, "Are you being serious?" Yeah. You know, like I thought he was like, you know, maybe joking or something, and he was like, "No," he's like, "I'm being 100% serious, and we'll have a pizza party on Tuesday of next week."
What?
From 7 to 9.
What, really?
Yeah, I know. I was like, dude,
Dr. Abubad?
That's what I'm saying. I know.
Wow.
Yeah, and I asked Lacey, I was like, what, like, how hard did you have to convince him to do that? Like, this sounds like a Lacey idea. And she looked at me, she was like, this was all Abubad's idea.
Wow.
Is to sit us all down, and like, it was cool because, I mean, he literally, like, we had the whole, not the makerspace, the den. Yeah. The den all to ourselves. We had pizza. I think it was like, it was good pizza too.
It was good pizza.
Okay, it wasn't even like Domino's or like, you know.
What was it? What kind of pizza was it?
It was like Empire. Okay. I don't know. It was one of those like.
Was it Dado's?
It could have been Dado's.
It's not Dado's.
Okay.
No.
I don't think so.
It had like a blank box on it, so it just said fresh pizza. So I was like, yeah, I know. I was like, I don't even know what this is from.
I tried it. It's actually good.
Yeah. So I was thoroughly impressed and just a little thrown off when he said that, but it was cool. He got to be our tutor, you know, went around the room. We were all in groups working on problems.
Okay, cool.
And he got to, you know, really like pour into us, and that's what I love it.
Is that how it was set up? Like, how was this like presented to you guys?
We didn't really know what we were going into, honestly.
Okay.
He was just like, you know, we'll just have a study night, and that's kind of all we knew.
And then he'll just say that it's pizza.
So you could or you couldn't come?
I mean, yeah, it wasn't required.
Okay.
I mean, Lacey was very adamant. She was like, "I want y'all to come because this doesn't happen a lot." Like, you know, like,
no, I've never heard of that.
Yeah, I know. So it was cool. I really like Abubad, bro.
So
like,
cool.
I can tell and that's why I like UCO in particular. Is I just feel like you go to any other university. The only other one I've been to is Texas Tech. That's where I started, and I feel like you're not going to get that you're not going to get professors like that are willing to set aside a portion of their night and actually pour into students and like be able to be right there next to you and have that personal like tutoring time.
Yeah, they want to go home too, but they chose not to go home. Spend the night. 7 to 9.
Yeah,
just
yeah.
Wow,
that is so cool, bro. It was so fun.
And so,
and it helped.
What chapter were you guys in? Where were you guys going over?
Nodal analysis, mesh analysis,
nodal and mesh,
superposition, Thevenin.
Okay, sort of getting into the harder type
the nuts
things.
and bolts.
No. This is. I think in electrical science, this is the hardest exam.
Yeah. It is. That's what I've heard. Like even like some EEs that you know are really really smart and are doing well in other classes.
Student mentors. They tell us
they're like,
y'all. The hardest one.
Like this is an extremely hard exam.
Yeah.
So
they even say don't. They even told me like don't beat yourself up if you can't pass this one specific one.
Yeah. So. That's hilarious. Wow. And so I'm always curious to hear, you know, if students did any. I say students, I'm a student. If you or fellow students did any studying over the break So did you do any studying over the break?
Oh yeah.
Okay.
I did some. I mean, not as much over the fall break. You know, like when we were watching football, on Jacob's couch. You know, I did a few problems, but it was really the time before and the time after. Like, you can ask any of my friends. I would even be in other classes.
That's dedication.
I would just be like, man,
I love that.
I want to get this stuff because I've heard like if you're able to do well in electrical science, that digital and analog and like circuits 2 is going to come a lot easier to you.
Yes.
So yeah, I was like, okay, I want just a good foundation, you know.
Yeah, well, I think I don't know how to get this across, right? I think it just sort of depends on each student, right? Yeah. Where they are in their learning process and everything like that. But man, if you just really try to focus really hard in class, right? Mm-hmm. And you're really paying attention and you're writing notes, like to me, the better you get at that, the less you have to study outside of class.
Yeah, it's true.
That is 100% true.
And with everything going on, right? Like sometimes you just don't get enough time to study. So really taking advantage of that time in class where you can ask questions, you can really try to understand. Of course, you're not really going to understand it because you're in class. It's probably the first time you've, seen the type of problems, which also one thing that I tell students to do is like try to read the chapter before you go into the class. That really that like for me gave me just leaps and bounds, or did leaps and bounds for me. But anyways, I love that you did homework over the break because that just shows like it's a dedication, right? Yeah. So I know a lot of students that didn't. I was like, how do you not? There's so much, especially if you're a full-time student. Like if you're not studying over the break, you're...
What are you doing?
Yeah.
What are you doing?
Yeah, exactly.
Yeah, and I get it, like it kind of depends on the class. Like sure, I think for me like math, physics, modern physics, computational methods, those are my other 3 classes, and they're not super time heavy. Yeah. But this one in particular, like, I know it's the nerves will get to me if I don't study.
Yeah.
If I don't have that time.
I mean, I get it, and because I hear it all the time. Well, I'm just so busy. I'm just so like, yeah, I get it. I'm so busy as well. Yeah. But you have to find the time. Like, no matter what. Like, okay, maybe I need to stay up an extra hour, right? Or you need to leave the party a little earlier, something like that.
Controller. Put the controller down, bro.
If you want to, because I liked how you were sort of. I don't know the right term for it, but almost like, and this sounds kind of weird, but anthropomorphizing the professor, right? Because it's like you need to build that like personal relationship with them so that they feel like a human to you, right? Yeah. So you have that like human connection because then you see, okay, this is like a two-way street. Like, so I need to do what I can to be a good student. And because if you want him to be a better professor, you have to then also be a good student, right? Yeah. You can't just expect all of this out of them and then not do your part as well. And then also just like it makes class more fun, right? Like you can sometimes you're just I don't know. I'll ask questions in class, sort of like sometimes personal questions to my professor. Like, Dr. Benjabar hurt his hand recently playing volleyball. And so, we were just in class and going over stuff and I was just like, dude, what did you do to your hand? And I don't know, I just think that makes the whole class experience
more human.
Yes, and is less tension filled.
Yeah. No, I know. I agree.
Yeah.
For sure.
Anyway, so how was your break? You did some traveling and...
Oh, yeah, no, I had to travel because I need to get some documents signed in the consulate. So I went to New York and Boston.
Okay.
Oh, wow. Dang.
And did you go to MIT or you just got
we did.
Oh, snap.
We went to MIT and Harvard.
Okay.
That was the most amazing experience I've ever had.
Wow.
We didn't have time for a tour. We didn't have time for to actually explore everything. But the accessibility of MIT, like anyone can just walk in, explore the halls.
Yeah, just like UCO, right? You just walk into,
Which is strange because Harvard, you can't do that. You can't just explore the buildings because those buildings are smaller.
Yeah.
And they're like chunkier. And they do have museums and accessible buildings, but at the time we were too late because we went by bus.
There's a museum in MIT?
MIT, yes, MIT has a museum, a few museums.
Oh, wow.
Well, we actually kind of have a musume here, right? I mean, there's a bunch of
Sort of,
artifacts and stuff.
A little exhibit, right? But they have a full-fledged museum.
Wow.
So Harvard has one too, but we didn't get a chance to do that. But MIT, man, that was insane. Because we went to a museum.
Yeah.
The museum has Claude Shannon's like actual stuff there.
Wow.
Like old technology, like the RAM,
father of information theory.
Yeah. All his stuff is there. A lot of AI robot stuff, like prototypes, the history of how it came to be. It's insane. And also, they have like visual arts museum that just opened on October 28th, so it's probably like in 4 days. But we couldn't make it, obviously. But the lady at the front desk was so kind. She was like, "Oh, are you guys not staying for the visual arts museum?" We're like, "No, we can't. We're leaving today." And she's like, "Okay, before you do, you better visit the Coop. And while you're here..."
The what?
The Coop. So every university, at least Ivy League universities, they have a Coop where it's like a store that's all just their merch.
Oh, okay, okay,
gotcha.
cool.
Coop.
Kind of like the bookstore here, or the
Yes.
Barnes & Noble or whatever.
Yeah, but it's next level. That's all I'm telling you.
Yeah.
But,
Of course, it's MIT. It better be, dude.
Yeah.
Harvard has a bigger one, I think. But,
Okay.
but I didn't get to go. But basically, she was like, "While you're here, why not I give you a ticket
Yeah.
that will for the visual art studio, the museum when it opens."
Okay.
And we're like, "Oh, but we can't make it though. We're already going back." It's like, "Don't worry, it's valid for an entire year."
Oh wow.
Oh,
okay.
nice.
So we just got free tickets to the new museum that hasn't opened yet.
That's awesome.
So hopefully next time, if I have enough money, I'll go back. But I have to start saving up.
Dude,
But God,
that's
That's so
awesome.
cool,
yeah,
bro.
it's amazing. Boston is as amazing as I expected it to be.
Yeah, but there's so much history there.
Yeah.
I mean, right, the Boston Tea Party.
Oh yeah.
That's like where really like the birth of our nation sort of started
The
in the
Celtics, you know?
Yeah.
All the
Thunder up, okay. I don't know what. Have you always been a Celtics fan?
No, I'm just joking.
Oh, okay.
do you
Boston
watch
Red Sox.
do you watch NBA?
A little bit. I mean,
Okay,
I watched the
yeah.
finals for sure,
Nice.
but I'm not like a huge basketball fan.
Okay,
Oh
fair,
my
fair.
gosh! Have you guys seen what's going on right now? There's a huge gambling scandal.
Yeah.
That the, like 3 people got arrested from by the FBI, like Chauncey Billups, Rozier, and one other, I think, player or coach or something like that.
Dang.
And yeah, not to, I don't want to go too much into it, but it's just fascinating, right? And it kind of makes me sad because I'm like, man, like I love watching sports, right?
Yeah.
And the last thing I want is to know that it's being rigged.
Yeah.
And apparently, Chauncey Billups, which was the head coach of, I forget what team, but he was the head coach, and apparently he was being paid by the mob.
Damn.
Yeah.
That's
Don't quote me, but I'm pretty sure that's the headline I saw, anyways.
There's gonna be a movie about that soon. I bet. It's gonna be a Netflix movie. Yeah.
documentary.
It's a Netflix movie.
Yeah, but anyway,
That's crazy.
Anyway, so MIT, I have to know more about MIT, man, because like that to me as a technologist, as someone who
that's a dream
Yeah.
school. That's a
That
dream school
is-
for all engineers and scientists.
It's like one of the hardest engineering schools to get into. They make you make what's called a maker profile,
Yes.
and you can go on YouTube and look at a bunch of these different maker profiles, and these kids who were just trying to get into MIT. Go ahead.
Yeah, no,
Go ahead.
they're in their teens, late teens.
Yeah.
And they're already making like robots and shit.
Yeah,
They
like some
made it all from
high-level
scratch.
stuff.
That is crazy.
All from scratch. They're
Yeah.
like, oh, this is just make up my MIT maker profile for,
Yes.
and I made this. The one I saw is like a drone umbrella that just follows him around.
And
when
some
it
of
rains,
these guys don't
crazy.
make it in, which is crazy.
Yeah.
It's like, I wouldn't even imagine having to build something as intricate as some of these maker profiles just to get into a college.
Dang, I didn't even know that.
And I mean,
Okay,
I'm just now getting to the point where maybe I can build something.
Yeah, we just started.
That is crazy. I wonder if they have any like intro tests like that you have to take like some math like what their
They have
math
interviews, stages of interviews.
Wow.
So they
Yeah, it's
review
a
your
whole
maker
process.
profile, the portfolios and stuff, interview you like a few times before you get to enter. And here's the craziest part. When you look at the website, like just any college website, right? Harvard and MIT is top one in their own leagues. So like MIT is obviously robotics and science. Harvard is like humanities, art, and med school. They're all top ones in their own leagues. But both of them have 0 to 10% acceptance rate. That means there are times where they don't accept anyone at all.
Wow.
Wow.
So on average, per year, on average, MIT has acceptance rates of 4.37%.
Wow.
Or something like that.
So
Yeah.
whenever I was thinking about going back to school and I finally picked like engineer as what I wanted to do, well, actually I was thinking I was going to go for computer science, but then I was thinking, well, maybe engineer. And so I was just like, okay, well, let's look up on YouTube about engineers and in college, right? And some of the first things that were coming up were these maker profiles at MIT.
Yeah.
And I was like, is this what I'm up against?
Yeah, no, that's crazy.
Now, I mean, don't get me wrong. I love that spirit, right? And you don't have to go through that to get to into UCO, but UCO is still like a great college to go to and learn from. It's just MIT is just a whole nother level.
It's there's ABET accreditation,
And then there's MIT.
I mean, that's the bar. Like, and then you keep just going and going and going.
Yeah.
There are
MIT's
levels to this game.
Number one, dude.
Yeah.
That's crazy. I bet that was so fun though, bro.
Oh, yeah.
Just I get to walk around and.
I was like, I'm breathing the same air as MIT students. and the craziest part is MIT has close ties with NASA and a lot of like government like projects like in the world. So it's like it's very interesting how they operate, and they're all very practical and they're all very transparent. They just ask you not to take pictures, but most of their labs are just glass. You can see right through.
They ask you not to take pictures?
Yeah, they'll have signs there. Please don't take pictures.
I would have been taking pictures.
Yeah.
Videos. I'd have been like, okay, this is me.
No, that's the thing. I wanted to take a picture of the material science lab.
Okay.
And then I want to show you.
Yes.
But they have the signs there. They have the sign all over the wall saying like, please don't take pictures.
What?
Please. So I'm like, okay, they say please.
Yeah.
So I'm like, okay, I'm not gonna take pictures.
Well,
and the camera's staring right at me.
Yeah.
See, for me, it's like, well, they don't say it's forbidden, so.
Right. That's funny.
Yeah.
But how did your papers things go?
Oh yeah, they went away. They were fine. Yeah.
What did you have to do? You just.
It's just because whenever you're overseas, whenever you want to sign a document, it has to be attested by your consulate or embassy before you send it back, because they need to know it's real.
Yeah.
Right. You just receive documents from overseas. They need to know it's from that person.
And why did you have to go all the way to New York for that?
Because there's consulates there. Malaysian consulate is only in New York, DC, LA, and the DC wants the embassy. So we have to go to these places just to get it attested. Be like, oh yes, you signed it in front of me. They chop it. Then only I can send it back home. Then they'll be like, then the lawyers in Malaysia and the court be like, okay.
And you can't just zoom it in, dude. Like,
that's what I was thinking, like a Zoom or something. Like,
No.
I mean,
No.
Yeah, like they give you papers there to sign, and you sign them in front of in front of them.
Here's the crazy part. They go to such extent. They analyze your signature to see if it's forged. They analyze the ink to see if it's a real pen ink that you sign.
Wow.
The chop and the ink from the consulate. They will analyze it to see if the chops are and the ink is the real one.
Wow.
If to make sure there's no fraud.
Yeah, of course.
Because legal documents are no joke, you know what I mean?
Yeah.
Any legal document, regardless if it's like inheritance, regardless if it's like, oh, you're just trying to get into another country, you don't want fraud. So
yeah.
I mean, I like the attention to detail there, but also at the same time, it sounds a little ridiculous. I mean, I get it.
Yeah.
And it's costly for you and your family too. I mean, you know, you gotta get a flight, you gotta go. I mean, that sounds.
I'm just saying it's worth it.
100%. Yeah, necessary for sure.
No, anytime you get to travel, you've gotta go, man.
No, I mean, I feel like if it wasn't for the documents, I would not be able to go to New York. It's too expensive.
Yeah.
For sure. Anyway, so
how's your week?
I mean, I think for the most part, it was a pretty chill week. For the break, I went over to, we have a little lake house out in Fort Gibson that we like to go to.
You told me about that, yeah.
Fort Gibson's like east of Tulsa. And our place is like maybe a mile away from the water. And it's just a nice place to just get away. You don't have all the sounds from the city, right? You just feel like fresh air.
Change of pace.
Yeah, exactly. But it's funny because it's change of pace in a way, but like I'm still just like.
Okay, yeah. You know how I imagine this? You know Schrodinger? Schrodinger, when he at some point he went to a winter getaway. Like he went to a cabin just to work. Yeah, just to work on his equations.
Oh, wow.
And then in that winter getaway, he discovered the Schrodinger equations for 3D solutions. Right? That's how he realized the atom. Like his paper, his thesis was on how he can derive the wave function, the Schrodinger equation, to derive the orbitals of hydrogen atom and molecules. And that's how I imagine what he does is every time he goes to Fort Gibson, bro, sit down. Starts hacking. Starts like hacking away.
I'll connect my machine to a screen, so I have a larger screen. And I just like two screening it up, and then just with my keyboard, just getting after some work, dude.
I bet see a bird fly, and he has this eureka moment, and he's like, "Oh wow."
It's funny, there is like a sense of like clarity that I get out there too, though, which is interesting. Yes, because. East Oklahoma there's a lot of trees and it's sort of hilly, right? So it's a lot different than here in the middle of Oklahoma, just flat and not a whole lot of trees. Like out where my parents live, out in Amber, Oklahoma, there's like no trees and it's just like flat as can be, and the wind's just pounding you every chance it gets. And I wish everybody could just have that feeling of just like getting away, just like every other weekend, being up in the trees. I used to not be able to work out there because I would just go out there and I just want to be lazy. I just want to like just relax, kick back. And then I got to a point where it's like, no, like it's like it makes working a little bit easier, actually. Like, I don't know, I just had to force myself to start working out there. But also at the same time, like being in the semester, you have to work. Or if not, you get behind.
Sure.
And like you said, your anxiety just starts to go through the roof when you start to think, oh, I've got a test next week.
Yeah, there's a lot more things I feel like that go into productivity than just like work ethic. Like there's a lot of things that add into, really like how productive you can be. And sometimes like having those, getaways and just getting away from the world and, being...
Like what we said at the beginning before this podcast is like sleep, right?
Hello, space travelers. Want to look sharp while bending space time? We've got brand new Physics Society t-shirts. The clean graphic tee is just $20. And if you want to drop some Einstein-level wisdom on the back with this quote, "I have no special talents, I am only passionately curious," that one's only $25. Rep your curiosity, rep the cosmos, and support the Physics Society. Grab yours today before entropy takes over.
And what you eat.
Yes.
Yeah, I know.
Well, I don't know if we've ever talked about it, but your gut and your brain.
Gut-brain axis.
Yeah, they're like connected
Hormones.
a lot more than what you may think, right?
Oh, yeah.
Like what you eat can dramatically affect how your brain feels, how which then affects your emotions, and right, like it's so funny because so you guys were talking about the pizza party that was Tuesday, right? And Iris comes up to me and like, hey, there's pizza downstairs, and I don't eat pizza during the week. I don't eat like a lot of carbs during the week.
Sure.
And then also for pizza, like I'm such a glutton. Like I can't just eat one piece. I have to eat like a whole pizza. But like I don't know if it's my age or whatever, but if I eat a piece of pizza, like I feel it the next day. So, like my brain is cloggy. It's Go ahead.
I really like when you eat clean and you don't have excess carbs for like a period of time. I went through the same thing. Here lately, I haven't been too, like tight on my diet. I've been a little looser with pizza and burgers and stuff. But when I was eating really clean, sometimes. Yeah, like when you have excess carbs, because pizza is just carbs and fat.
Yeah,
there's really no protein. There's and it's not a healthy balance. When you're like, I know exactly what you're talking about. Like your body goes into shock because it's actually not like ideal. It's like your body is like, whoa, like there is so much carbs in here. So there's insulin spikes and it's kind of interesting how your body like reacts. If you are eating clean for like a period of time, you have that pizza one night, and it's and you wake up and you're like, I just got hit by like a small bus or something. Like what is up with So it's cool. I've had that same thing, but just your body like
Yeah, it's weird. It's like. It feels like a hangover to me now, And so like I don't know. It's so weird because I'm starting. I don't know how to say this, but anyways, like I just keep cutting more and more out of my life, right? Like I don't drink anymore, and I try to eat as good as possible. Like I do love I have like a piece of cake or like a I'm really bad because like I'll be really good Monday through Friday or really Monday through Thursday to Friday night. But like the weekend will hit and I'm just like, ooh, where can I go get me a piece of cake? Like I'll go to like La Baguette and pick me up like 2 pieces of cheesecake or like a variety of like baked goods and stuff like that. And then I'll just go ham on it, and then the next day I feel like crap, and I'm just like, I've got so much work to do today, though. And it's interesting. You don't really know how it affects you until you try to cut it all out, and then you start adding stuff back in. You're like, oh wow!
It's like that feeling, like that tiredness and kind of hungover. That's actually a good thing. Like the fact that your body feels that way proves that, hey, like you are doing the right things. You're eating right.
Yes.
Like, it's not because I remember seriously, I was eating really clean for like 3 or 4 months. I didn't have like any pizza, any sugar, anything.
Wow.
I know it was for a long period. Yeah. And I had pizza one day. I was at work.
That's some discipline, dude.
Yeah, I know. Yeah, and it really. I need to get back into that, dude. Like I said here lately with ES and with everything else, I'm like, all right, let's get a pizza.
Yeah.
But yeah, like really, because I looked at, I was like concerned. I was like, why do I feel like so bad? And and I was reading. It's like, hey, that's actually a good thing. Like your body isn't supposed to really eat pizza. Like you're supposed to have the fats and the protein and the carbs like in balance. So it was kind of a breath of fresh air. I was like, okay, I don't have diabetes.
Yeah, you started to think of it like a scientist, dude. I like it. What is that, like falsification or what do you call it, induction, right? Where you're starting to deduce all the different things that it could be, right? That's science in the making right there. I love it. Well, I think this is a good segue to get into our topic for today, which is quantum mechanics.
Modern physics and quantum mechanics. Let's go.
Which honestly, man, like we were talking about before, quantum mechanics, it sounds like this weird, elusive creature that comes out at night and is like ready to just pounce on you and take you back and drag you into its dark hole. But like what we were talking about, like
sounds like some eldritch being.
The Loch Ness monster.
It can sound scary. It can sound scary, especially if you haven't I don't know, if you didn't go to college to be an engineer, for instance, like, because once you sort of start to take harder classes like the calculus, the electrical engineering, the differential equations and things like that, you start to see like, oh, like, all right, I can do hard things. I can do some math. I can do some hard math. Let's go. Let's get it. And then you run into quantum mechanics, and it's like you throw all that stuff out the door, like all the stuff that you've learned. For me, anyways, this is how it was. Like, I still just like approached it like a little scaredy cat, like a Schrodinger cat.
That's me. I'm Schrodinger's cat.
But man, like,
I think that's the beauty of quantum mechanics, right? You both know and don't know at the same time.
Yes. Yeah. But, you know, it's just like, it's just, you know, like every other subject out there. And yes, there are the things that people will say, like, if you think you know quantum mechanics, you don't know quantum mechanics, which is like this weird saying that's like every engineer's nightmare, right?
Yeah.
But at the same time, like, it's just another model that you just have to spend more time with in order to start to get an idea of what's going on, right? There still are some things that are very elusive, right? But at the same time, like, you find out, oh, okay, well, this is some probabilities, and it's kind of has some flavors of signals and systems in it, because you're thinking about the different, because it's the Schrodinger wave equation, right? And we deal with wave equations in signals and systems. And you sort of hear about sinusoidal and cosine waves and how they come together in like calculus and differential equations. But at the same time, you just gotta go for it.
I agree.
And for me, quantum mechanics is like the most, for me at the moment anyways, is like one of the most interesting topics, because I feel that, for one, so my research is in material science, right? And in order to understand materials at the atomic level, you have to understand, or try to understand, quantum mechanics, right? And so I feel by learning quantum mechanics, you're learning the fundamentals of reality. And because, you know, like in physics 1 and physics 2, you're like, okay, yeah, you're familiar with these things, right? Like, I've rolled a ball down a slide before, and I've crashed a car into a brick wall before. I know how forces and things like that work out, right? But then you get quantum mechanics, you're like, okay, this is a whole nother animal.
Yeah.
And you start to think about the atomic level and how those things are interacting to then, you know, all those interactions then arise to these like quantum properties and things like that. But anyways, I think we start off. Sorry. And so one of the questions you asked is, what does quantum energy even mean? Right. So I think, if you can, anyways, maybe try to explain it in your own words, if you think you can.
Okay. I mean, well, when I first think about energy in general, I'm thinking of, you know, gravitational potential energy. I'm thinking of kinetic energy. I'm thinking of joules. You know, I'm thinking, that's like where my mind is, I feel like, kind of just stuck in right now. Like, I'm stuck in, you know, PSE 1, like physics 1, and I'm like, well, I got the ball, and Teo's over here throwing a tennis ball. You know how he does that? Like, and so when he talks about like how, you know, an electron or a photon can have different levels of energy, and he kind of starts describing that as a quantum property, you know, that's just, I'm really lost. Like, you know, we had a virtual lab where you basically, in modern physics, where on your computer, you shoot an EM wave at an electron. And you have to, you know, pick the right one in order to get it to move to a certain orbital. Like, you know, like and so it shows that energy can be like absorbed by the electron. And I know that's, you know, touching on all the right aspects, but it's just, I don't know. I feel like I'm really stuck in classical physics. And if I had to describe quantum energy, I would say, okay, maybe I would say it is finding and describing the different energy levels that subatomic particles are able to have. and how they get to those levels. Like, you know, that I guess that would be my
I think
That's basically it.
yeah. I mean, that's what I figured. You know, like, but
so like. What makes you so interested in quantum physics? Because I love that you were, because this is our first student podcast, right?
Yeah.
And, you know, I've talked to a bunch of students on like what they would like to come on and talk about. And you said quantum mechanics or quantum physics. I was just like, let's go. Pick one of the hardest things. Let's go. Because I'm always down to like
Dig into it,
especially the things that are like considered one of the hardest things out there, right? To try to understand.
and he's like, bet.
Yeah.
all right.
Yeah. So well, what interests you about it?
So,
Or how did you come about it? Maybe.
I mean, really, like, I don't know. My curiosity about it kind of just stems from, like, I really want to understand when I looked up, you know, what, you know, quantum is and studying quantum mechanics, quantum physics.
Yeah.
A lot of the answers that I get is about the probability of an electron in the cloud, right? Like, there is an infinite number of different places that electron can be, you know, and it's like kind of pausing time for a moment and saying, at this moment of time, that's where the probability is. And I think like what I would be like passionate about learning is kind of boiling down how on earth does like pinpointing where an electron can be, how does that affect the world around me, you know? Because I hear it in class and sure, it's interesting. I'm like, dang, like that's so cool that we get to use these equations to kind of do that, you know? Like, he gave us Schrodinger's equation on the board for the first time the other day, and he was talking about the psi function. And he was like, "This is the probability function. Like this is a function." And I don't know. I feel like that's where my brain is always at. Is like, what is that going to do for the computers in front of us? For like how we can advance, you know, communications, like. You know, what does that do? What do you guys think? Like, what does that do for us in our daily lives?
Yeah, I mean, as an engineer, that's the perfect question to be asking.
Yep.
Right? Because that's what engineers are supposed to do,
Engineering is
right?
applied sciences.
Yes,
You want to apply the knowledge.
Right, exactly. I want to apply this, not, you know, just kind of learn about it. Give us a few equations. And I get it, you know, professors have got to put that stuff on the board and kind of let us gnaw on it and chew on it.
Yeah.
But I'm always like, I don't know, like what is going on? Like how is this going to help me? So
Yeah, no, most definitely. I don't know if do you want to add anything here?
I mean, for me, in my opinion, a lot of the scientific discoveries like start off as not about application because they're pure theory. They're like for example, Einstein, when he discovered the photoelectric effect, he's not gonna be like, someday it's gotta be for laser surgery, you know? Like, no, he's just like, electrons, specific wavelengths cause them to kick off. No matter how bright the source is, if it's in the wrong wavelength, it will never emit electrons.
Yeah.
So that this discovery allows them to realize, okay, can we focus all these beams of light that comes off that material? And if we can, how? You know? So that's eventually led us to discover how to make specific photo detectors because different energy levels, right? So we can detect specific wavelengths. And then also gives us an idea of spectroscopy.
okay.
Spectroscopy is like, you know how different materials and different atoms absorb and emit different wavelengths of light, right? Well, even though this discovery is a long time ago, Newton and a bunch of different people already knew that different materials emit and absorb different wavelengths. Now we know the why and how, and we can do it even more detailed. So allowing us to do more modern day of spectroscopy. So I feel like all these theories, once it goes into the hands of engineers like us, that's when we come into play and be like, that's when we started just thinking about, what can we apply this for?
Yeah, it's, you know, so your question sort of gets at also the question of like, what is technology? Because so humans in general, right?
True.
And I love that. So Tej gives a talk about material science, and it always starts with like a rock, and basically like the prehistoric humans, right? Or I don't know how you would call it, but the very first humans, right? They come across this rock, and then they start to manipulate this rock to be able to they sharpen it and make it into a weapon. To which that for them, and that is a technology, right? And so us humans are these things that are able to manipulate our environments, right? And engineers take that like to the next level times infinity, right? Where not only are we just looking at rocks and how we can manipulate those, but we're also then trying to look at the atomic level and like what can that do for us to help us progress our technology, right? And because I think at the end of the day, like engineers, what our job is to create new technologies that further the progression of human evolution, right? And to help our lives easier so that we can do more cooler stuff.
Solve more problems. And help people too. Like create things that like, how does this help the world? How does this solve problems? That's what I love about engineering, honestly, is that it gets down to the fact of like, I have all of this knowledge and information. Now, how can we apply it to actually help someone every day in their life? Or maybe one, I mean, who knows, just to help people, that's what I really like about like what we're being set up to do.
Yeah. And so, so computer, all the computers, they're made thanks to transistors, right? And so you ask like, what is like the application of quantum mechanics, right? And so one of the things that first comes to my mind is transistors. And so, okay, so let's think about it this way. Like, so you have an LED and you want to make that LED turn on, right? You want it to light up, right? Well, you can just put a voltage source to it, and you can start at 0 and start to crank it up, right? And once it hits like a certain threshold, thank you, that LED then starts to light up, right? Well, that's a simple circuit, but then what if you then add a transistor to that, right? What if you want it to only go on sometimes, right? You want to add a switch, right? And so what you can do is you can, these transistors is they have a threshold voltage, right? Some of them are higher and lower than others, right? And the reason for this is thanks to quantum mechanics. And so essentially that acts as a switch, right? And then that's what computers are made of, is billions of these transistors, right? And then you think about so like how computers then know what to do, what they're going to do. Well, a bunch of these transistors are in some type of silicon, right? And depending on the pattern that is created, depending on like how much voltage is given here and given there, that's what the operation then is going to be at the end of it, right? And so that's sort of their language, is like these, the patterns of the on and off switches of these transistors, right? And so you get into these transistors and they take advantage of these quantum mechanical effects, right? Like tunneling and things like that. And so I'm trying to, so there's two different types of transistors. There's the N-type and the P-type, right? And so the N-type, your carrier is the electron, right? And so this is what they say, is that your carrier of current is the electrons, right? And then in the P-type, your carrier of the charge is the holes that are sort of left behind from electrons moving. I believe this is the right way to think of it.
So when electrons leave an orbital, they leave a hole.
Yes.
Because there's an excess positive charge there.
Right. We learned that just yesterday. Actually, you are literally touching on exactly what Teo was talking about in modern physics the other day.
Okay, awesome.
And about what a hole means. And what I thought was cool, he said that when an electron goes from one band to another, an electron fills a hole. He was talking about like annihilation, you know, and how it becomes annihilated.
Okay.
The electron itself, like, because he was saying that in order for it to go from one band to the other, it emits energy.
Yeah.
In LED specifically, light. And so like that electron, it's because like E equals mc squared, mass and energy are now related. It releases all of its mass as photon, and that photon is at a certain wavelength based on how far it traveled in the band gap. And so it was interesting, you know, to learn about those like holes and like what a hole is, you know, like he said that a hole was something really that is entirely abstract and made up. It's not really there. It's not a real, like, you can't, you know, point to it and look at it, but
it's sort of the electrons
shadow.
Well, like the electrons' distance or relation to the valence or the
conducting band.
Band.
Yeah. So a nuance and a caveat to that. He's using a metaphor because in solid state physics we have a term called effective mass. So basically, in solids, electrons have different mass than it would be for a free electron.
Okay.
So the effective mass is getting converted into the perceived energy when it falls into the hole.
Okay.
And that is what emits the light. So imagine you have a hole, an orbital here, right? An ion here. So, because it's positive and negative, right? So it's a diode, right? So an electron will leave. And then when it leaves that semiconductor, it leaves a hole. So because it takes energy, right? To leave.
Right. Yeah.
Now, another electron comes in from the negative side. It goes into the hole and it's carrying energy. So when it goes in, it emits the energy. And then it gets pulled out again, pulls in, pulls out, pulls in, like a conveyor belt.
Yeah.
So that's what creates the LED voltage.
Wow. Okay.
Yes. So they have a term for that. So a hole is a quasi-particle.
Okay.
A particle that's emergent from a subsystem. It's from a system itself. It is not its own particle. However, because of the quantum behaviors of like how energy levels fixed, when an electron leaves, there's still an empty energy level there that is still quantized, and that quantized energy level acts as a whole.
Oh wow.
Yeah,
Okay.
so that's why you will hear phonons, which is quasi-particle of sound.
Yeah.
Even sound has quanta to it.
And so this effective mass, right? We were actually just learning about this the other day in solid state physics or solid state devices.
By Tej, right?
Yes. And I know some people don't really like Tej's, how would I say, teaching style.
Sure.
But to me, he's like, I think he's one of the best at explaining things. And so we were learning about this effective mass the other day. And there are some situations where the mass of the electron goes negative.
Wow.
Yes. Yeah. And so I was looking this up earlier because I wanted to pull this up and I wanted to talk about this because to me it's like one of the most fascinating things. Like, what do you mean it has a negative mass, man? Like what? Yeah. And so I pulled some stuff up. So electrons do not possess negative mass in the conventional sense, right? But they can exhibit negative effective mass, which we were talking about in specific contexts such as solid state physics. Particularly within semiconductor band structures, like we've been talking about. This phenomenon arises from the curvature of the electron energy momentum relationship and is described using modifications of the Schrödinger equation application to periodic lattices. So it's essentially, you know what a parabola looks like, right?
Sure.
It's a curve, right? That goes from the negative side to the positive side. Both reaching up, right?
Sure.
It's like if you're doing the YMCA, right? It's like doing a Y, right? Yep. So you can think of there's a positive YMCA and a negative YMCA, right? And
that's a good way to put it.
so when this mass is negative, all it's saying is that it's on the negative slope of the Schrodinger equation. Yeah, I think that's the right way to think of it. It rises from the curvature of electrons' energy momentum relationship. Yeah, so this energy and momentum is a curve, and whenever it's coming down, it's a negative curvature, or it's a negative slope.
Right.
So that's why it's called a negative mass.
So the x-axis would represent mass, right?
The y-axis. Right.
Well, because if the only time you can have a negative derivative on a parabola is on the negative side, like the negative x side.
Yes.
Like once you reach the origin, then you get to positive x.
You gonna draw it out?
Oh, sure. Go right ahead, dude. Yeah. Here, I got a marker.
So
no. Let me give you a nice.
I just want to know.
Here, let me give you a nice one.
A nice one?
Yeah.
Oh yeah.
that does look like a nice one.
Yeah, it's a nice one. Dude.
So I just want to know what you're talking about. So you said that's like an x-axis and y-axis.
Yes.
So it's like this, and then you said this is the Schrodinger equation. That's also a negative one.
Yep.
So what? So what were you saying? Can you explain that
Okay,
again?
so
when it says the negative mass is like when it's right here, right?
Oh, I could have swore I had it pulled up. Let me see if I can pull it up really quick in this chat I had.
I feel like this is where stuff really comes to life for me. Is when I'm able to look at a graph of something and start making sense.
Visualize it.
Like that right there. You know,
here
like
it
this. I can visualize what's happening. Like
yes.
Okay.
So it says.
Band structure. I got you.
Yes. So.
Okay. So you're talking about the band structure specifically.
Yes. So let's see if I can. In a semiconductor valence band, electrons near the top have negative effective mass due to the downward curvature of the energy band. Oh, okay. So I think it's actually talking about the whole. Okay. When such an electron is excited into the conduction band, it leaves behind an empty state, and that's the hole.
yeah.
Yes. Yeah. So when those are like really close, right?
Semiconductors, right?
What's that?
So that's when the semiconductor. You need energy.
Yeah.
Into it.
Yeah. And so right there is where you would have a negative mass, is where those two meet.
Oh, it's where those two meet.
Oh. Yes.
Okay.
I'm pretty sure.
Because so here's what the consequence. Okay, let me just go back to the micro first.
Yeah. So let me just read this really quick. Yes, the condition. So the second derivative of energy, less than 0, corresponds to a downward curving energy band in a semiconductor, which occurs at the top of the valence band. This curvature indicates that electrons in this region have negative effective mass. Yeah. And so really, from what it seems like, right, is it's really just a consequence of the graph.
Yeah.
And the graph is a consequence of the system itself.
Yes.
Yes. So the consequence, the actual real physical consequence is that whenever you have a charged particle like an electron in the solid state material, when you have an electric field or a magnetic field, normally you will assume, for example, electric field pointing this way, an electron will go towards it, right? A electron with a negative effective mass will go the other way. That's it.
Oh wow.
So it just responds the opposite way.
Yes.
Like an antiparticle.
Yes,
So,
and that's what's
yeah.
weird is it's going towards the direction of the voltage source,
Yeah.
which is sounds counterintuitive.
Which is against all.
But in reality, it's not. It's just that there's a probability that some will do that and some
won't.
Yes.
Will not. Yeah.
Wow.
And that's a good way to represent this is the whole.
Yes.
The whole is also moving from part to part, and the way the whole moves is, look, this is a hole, this is an electron. When the electron moves here, it leaves an empty spot here, right? So the whole it looks like it's moving here.
So
Yeah.
So the way to think of this, right? So whenever you dope a material, you're essentially you can dope it in two different ways.
Yes.
You go right ahead,
I
Doc.
love that we're talking about this because semiconductors is the reason EEs have to take this class.
Yeah.
You know, it has to take more physics
Semiconductors
to understand
is
semiconductors.
one of the most interesting ideas. So, and it's the application of quantum mechanics.
Yeah.
So, in whenever you dope silicon with phosphorus, you give an extra electron.
And it's a free electron.
Yes.
It's free. Yeah.
Exactly. Yes. Free meaning it's it can move around easily
within the material itself.
Yes, exactly.
And, for example, if you dope it with a group 3, like let's say, what aluminum? No,
What's called it? I actually have it right here.
Aluminum? No, it's not aluminum.
Sorry.
It's, what's on group 3 again?
P-type phosphorus and silicon, which are I think I have it pulled up somewhere.
N-type, we need it. Boron and aluminum. Yeah, boron and aluminum.
Okay.
So for example,
Which are trivalent.
yes. So right now, what we see here is a P-type because you have an extra electron. N-type because an extra electron.
Yeah.
We need a. So whenever we put in an aluminum or boron, right?
Okay.
They have a lack of electron, so you have a hole.
Yes.
Oh yeah.
Yes.
So whenever this electron, let's say an electron from here moves over here, right? It'll occupy that space, and this becomes a hole.
Yeah.
So it looks like the hole's moving.
Yeah.
It looks like the positive charge is moving.
They're both moving at the same time.
Yeah.
I mean, you get one in one spot and the other at where it left. I mean,
yes.
Yeah.
Yeah, and so.
So usually, what's it called? The effective mass is a factor multiple of the rest mass. So the original electron's mass.
Okay.
That's why it can be negative, and it can even go to the 1,000 times. That's why we call heavy fermion materials. And I believe cerium is one of them, right?
Heavy, yes. The heavy fermion property or whatever it's called. Yeah, it's essentially when like an atom will seem heavier than what it actually is. And in this case, it's almost like it's a lot less than what it really is, right? The negative mass is what I'm thinking.
Right. Yeah.
But yeah, and so I forget.
There is an element. It's either Einsteinium or Berkeleyium. I forgot which one it is. That has because of the way the electrons orbit. It was that one of some of the electrons orbit so fast that relativistic effect starts kicking in, and the element's mass is heavier than expected. I forgot which element it is, but yeah.
Interesting.
Man.
Well, and so yeah, I mean, and that's what's kind of interesting is it seems like the future technologies are going to be able to manipulate this atomic level even better, right? I mean, right now we have a good understanding of what's going on, but there's still a lot of holes to fill.
Yeah.
Right.
I mean, it is filling holes for me, because like in order to determine anytime, like we learned that an electromagnetic wave is emitted anytime there is an acceleration of charge. Anytime charge is accelerated and moves from one point to another, an EM wave will be emitted through the air and through vacuum.
Yes.
Right? No medium. And so, I mean, this is really hitting on the why is the study of quantum mechanics. What does it tell us? What does it do for us? I mean, like, what color will that light be? Will it even have a color? What kind of EM wave is emitted when we dope certain materials?
Depends on the.
It depends on how far did the electron travel? What was the frequency at which it was emitted from? And so then you get to this thing. I'm really glad you put that up because
Which for the listeners or even people watching, we've been trying to do what we can to figure out a better way to share screens. It's honestly a headache to have to do. It's a lot of extra editing. But anyways, just Google electromagnetic wave, and that's what we have pulled up over here. And so
It's just a graph.
it's a graph.
Yeah. Do you want to explain it?
Oh,
the graph?
Oh, basically we have a. Do you want me to draw it?
No, it's fine.
Okay, so it's basically it has two axes, one for magnetic field and one for the electric field vector, and basically, as you know, with the left hand rule, or was it the right hand rule? Left hand rule, I'm pretty sure.
I can't remember from BSC2.
I'm pretty sure it's the left hand rule, but basically.
I think it's the right hand rule, right?
Oh, right hand rule.
It makes
right.
sense to be the right
hand rule. It is the right hand rule. So basically.
What's funny is you always look dumb doing it, no matter what.
You'd be like, what? Yeah. So basically,
I really think it's probably more of a joke.
Yeah, it really is.
So every time there's a change in electric field, it's not which can either come from acceleration, deceleration, or changing in direction, because it's a vector field. So a change in vector and magnitude can affect the scale of this, and basically, that whenever there's a change in electric field, the magnetic field will follow, and it's just so when there's an increase in electric field, magnetic field will increase, and then when the decrease in magnetic field, electric field, the magnetic field decrease,
and that's Maxwell's equation.
That's from the Maxwell's equation.
That's what proves that.
And and then they can start like affecting each other. So the magnetic field can generate electric field can generate magnetic field, and this creates a wave. Yeah. And this wave is what we called a photon, an electromagnetic field. Electromagnetic wave.
Yeah.
Yeah.
Okay.
Yeah. And so I'm trying to think of what would be the application of electromagnetic wave?
Well, everything. So if you look at it, like the lights we have, radio.
The people listening to this podcast right now,
yes,
they have a circuit somewhere that's built to pick this electromagnetic wave
transceiver,
up, from a server.
Yes, if you look at the old days, right? Oh my God, I have to draw this out. So basically, in the good old days, when we have those long antennas, so the reason
my truck has one.
Yeah. But basically,
those are the present days for me.
So when basically what you have is electrons shuffling up and down, back and forth.
Yeah.
And that creates a changing electric field, and hence changing magnetic field, and vice versa. That creates the radio waves. And when a radio wave has a resonant frequency as the what's it called, as the antenna, it will start wobbling those electrons, and your radio picks it up, and the amplifier turns it back into sound.
Wow. Yeah, one thing that I never thought about until just the other day. Whenever I saw this, I think it was just like a meme or a GIF or something. But they talk about like, you at the moment, let's say you have a radio and you're listening to, I don't know, 103.5 or whatever, right? Yeah. Well, you think that, I'm picking up this one radio station, but in reality, all the radio stations are in that room with you.
Yes.
Which is mind-blowing.
You're just tweaking the resonant frequency that your transceiver can and cannot pick up.
And that's an oscillating circuit, right? Yes. That's what that's called, like the circuit that's in your radio that you listen to your music on or whatever it is. Yes. It's an and it just like my understanding is, like you said, your antenna, it vibrates the electrons in your antenna at the same frequency that wherever the EMF is being emitted from at that same frequency, and it then allows you, like you said, that's okay.
Yep.
Sorry. Sometimes I just gotta, talk it through. Like,
for sure. Yeah. That's why we created this thing. We want to have a place where we can talk through these ideas because, for one, they're complicated. Yeah. Right. And then two, it helps you in many ways. Right. As engineers, we're gonna be communicating our whole lives about what we're working on, right? And the ability to communicate what we're working on in a way that's interesting to others is what really matters, and and the only way that you're going to be able to get somebody to listen to you is to say it in an interesting way. Right. And sometimes, like sometimes I will say, well, I don't want to have to explain all this stuff to them, but and I maybe like will lose them because there's a lot of like very intricate things I have to try to explain. But to me, like the complexity is really the most interesting part of it, right? And what a lot of like science communicators now are like trying to say is don't try to dumb it down. Like keep the complexity, because the complexity is what really is the interesting part about it. And also, you can't really explain something complex in a non-complex way. You have to have that complexity in order for someone to fully grasp what that thing is. And so that's why we started this thing, because for one, I want to get better at communication, and two, it's fun.
Yes, that's the main part right there.
And then three, we wanted to bring on students, we want to bring on professors, because we feel like the most interesting people are the ones just right around you. Right. Sure. And because I think for sometimes we get so caught up in social media, and we think that the most interesting people in the world are the ones on our screens. But really, if you start talking to the people around you, you're like, oh wow, like you are very curious in a bunch of different things that I've never heard of, and that may spark like something in you. And then at the same time, like there's a time where I didn't talk a lot, and because I thought that, well, whenever I talk, just nothing makes sense, right? But like you start to realize like, oh, it doesn't make sense because I haven't really talked it out loud. Like a lot of times whenever you talk things out loud, you realize sort of where what you're missing. Right. And you realize, oh, like, why do I think that? Right. Because it's interesting. We sort of think in images, right? And then we try to communicate those images. And the only way to get better at communicating those images in our head is to just do it.
Just do it more.
Yeah. I like what you said, like, like that realization that you had, like, hey, I can really learn from anyone, like everyone is interesting. Everyone has something that they can add value to my life somehow. I can learn something from you. I'm curious about you and what you know. Like having that attitude. I went to this thing called Leadership. Have you heard of Leadership at UCO?
I'm planning to go to the next one.
You're gonna love it, bro. It's really, this is hitting on all the notes that we did at Leadership. It was really fun. There were some parts that are a little corny,
Yeah, of course.
You gotta have those. Yeah. But it was cool.
The small talk.
Yeah, right. But one thing I took away from that, like, is that, like, being curious about other people, there's also like a kindness in that, like the people that aren't really kind towards others, they're not very curious about what they might have to say.
Empathy.
About how they think, like that. There's like a, having that kind of like hunger and wanting to know, hey, how, like, what are you interested in?
Yeah.
How can I learn from you? And having that kind of hard and like attitude towards people, like it's hard to be like rude and to be so shut off. Like that's kind of part of what rudeness is versus kindness.
Closes yourself off from so many different things.
Exactly, and you're missing out on so much more than you realize. So yeah, I don't know. That just reminded me of that. Like keeping that attitude towards people, like you are interesting and you have something to learn.
Yes.
Like it goes with kindness.
Yeah, I mean, I can be shy sometimes. I can be an introvert sometimes. But the best times of my week and my day and my life are times like this, where I sit down and have a conversation with people, or I meet somebody new and they spark something in me, or they introduce me to a new idea, and I'm just like, I gotta go learn about that. Because that gets back to like, what gets me up in the morning is like learning, and sort of like exercising this brain up here, so that so that I'm able to think deeper about quantum mechanics, material science, and my research, and because to me that's I don't know. I just have tried to find the thing that I love in life, and you only can find the thing you love in life by just exploring and just poking and prodding and really doing the scientific method on life.
Oh yeah. Yeah. And just that, like, having a passion. Like, if someone were to ask me, like, what I'm most passionate about, I'm passionate about a lot of things. You know, like there's some specific things that people are passionate about, but I really think, like, and especially in today's world, it is very important to be passionate about learning in general. Like, I think everyone should be passionate to learn, because when people aren't passionate to learn, I do think bad things happen when people just kind of just whatever and, kind of just idly go through life, like be passionate about learning things, whatever it is, whether it's quantum mechanics or fishing or whatever, And so it's nice to sit with a group of people that also just have that passion of learning.
My girlfriend said something to me the other day that just it just turned on a switch in me. So she said that you are there too, like everyone around, they have to deal with you too. You have to deal with them. So they have to deal with you as well. So just be you, because they're being themselves, and maybe they're aggravating sometimes, maybe they're whatever. But like at the same time, like, I don't know where I'm taking this, but just because there's like a sincerity in being passionate, and I think that can rub off. I think it
does rub off.
And so I think if we want more of that in life, we need to be the purveyors of that. We need to rub our static electricity on somebody and like say, hey, get this to rub off on you, right?
Yeah. It's hard to be like really passionate and excited about something alone.
And also,
like if it's just you.
And it's hard to be passionate without being yourself.
Yeah.
Like, how can you be passionate without being able to express it? And when I feel like expressing your passion is the highest form of being yourself. Because that generally comes from deep down, you really interested. That's why they say there's the burning passion, right? It's really coming from the deepest part of you. And I feel like your passion really shows that. And I feel like I think this is also poetic. If you have companionship to share with this passion is compassion. To be able to share other people's passions and understand people's passion, that's compassion.
Yes.
That's passion with company, with companion, compassion, I feel like that's kind of poetic.
And I think sometimes, getting to know new people or just talking to people in general, I think sometimes you can think, well, especially if you think in your head, you have this idea of them that you guys are like complete opposites, right? But really you find out that you have, all humans have a lot of things in common, right? And
it's just a negative bias. We just focus more on the differences than the commonality.
Yes, and we just gotta. I had something and then it just whoop. But anyways, you just gotta go and talk to people, and yes, So, how do I want to say this? So there is going to be tension no matter what. Right, you're gonna find even your best friends have ideas and beliefs that are totally opposite of yours, right? But at the same time, like, why make that the reason why you can't hang out on Friday?
I totally agree. Yeah.
Right, and I think there's because of the political environment or whatever, there's a lot of that. Or even just like, I don't know, there's just I want people to feel like, okay, you can voice your opinions, you can voice the things that you believe in, And no, maybe sometimes we may not agree. Maybe sometimes, one of the other persons has maybe thought about it a little bit deeper. Maybe somebody has a different philosophy, a different way of going about looking at things. But at the end of the day, if you guys are talking it out and figuring out like what are your differences, and you're okay to have differences, like that is like a part of growing as just a human being.
Yes.
Because I think it's essential for you to be friends with people who you don't agree with.
Yeah.
And it's essential to talk to people that you don't agree with.
Sure.
Because why would you? I mean, like for instance, like I don't know. There's maybe something that me and you don't agree on, right? But at the same time, like we have this, this sort of same curiosity and sort of the same sort of realm that brings us together, right?
Yeah.
And we could focus on the things that we, are different in, right, and disagree in, or we can just sit here and have fun and enjoy talking about the things that we do agree on, right? And we enjoy. So
no, I agree. I mean, like you said, at the end of the day, like not everyone thinks the same way that you do and has the same beliefs. But when you keep that mindset of like, hey, I may not agree with this dude on everything, but I still want to, be kind to them, and you have that curiosity about them and who they are, and like that kindness is right there with them, so you can still be kind to those people. You don't have to immediately start building up walls, and say, okay, like sure, you may not be best buds with the guy. I mean, you may not be like his best man at his wedding, but you can still have those like sharpening conversations and so I agree. I mean. Yeah, so
in science, we almost have to love being wrong, because
we'll always say something wrong, and that's how we learn. Because important part of research is the literature review, and that is basically looking at what you're planning to do and look at what people have been doing to correct yourself and to catch up to date, so that you know what's wrong and what isn't yet, and what hasn't been proven wrong. That's the whole beauty of science, is knowing that we don't know a lot of things, but there are things we've already proven wrong, and there are things we've proven right, and there are things we may never prove.
Yeah.
I mean, we're scratching at the surface.
Yeah. Oh yeah.
Like of everything.
Go ahead.
That's why I'm so tired when people say, "Oh, we are at the end of physics." No, we have so many things we don't know about physics. It's just because we have like those people that say that. They probably have not studied physics because they haven't reached the cutting edge. They don't know what we actually don't know. They think we know everything. We don't. If we do, we'll be having flying cars and shit. Like we have everything.
I'm afraid every day that I'm going to be wrong about things, right? Like in class, I'm all like, I raise my hand and I ask questions all the time. But at the same time, I keep in the back of my mind, like, this is how you learn, right? You've got to be wrong about things. And, there's definitely a fear that comes with being wrong about things, and I don't know how you get over that fear, but I think doing something like this is how you get over it, right? You face them and just like let's do the damn thing. Let's talk about quantum mechanics. So thinking of that, what have you been typing over there? I feel like he's been doing a lot of research over there.
No, I'm just because remember how we were talking about like effective mass and relative and all that. That's related to a lot of like modern physics stuff, like relativity, relativistic mass, relativistic energy, and all that. So I'm just reading more into it. So I listen. So here's a weird thing. I cannot multitask, but in a weird way, once I'm focused on something, I can listen in better. I don't know how that works, but basically, if I just try to focus on listening to a teacher, for example, I would zone out. I would have to be doing something, letting my body do something, letting my eye do something, and my ear do something else. In a weird way, that's multitasking.
Yeah.
But at the same time, it isn't. I don't know how to explain
See,
it.
that's where I have to have like no distractions. I hate when people talk in class. I hate when people are like fidgety. I hate when people are like on their phones
I
in class.
have to move around.
I have to like just. That's why I sit in the front row at every class because I have to like
Lock in.
Yes.
Yes.
I'm over here like looking left and
'Cause
right
I
because
get
I'm usually
distracted.
the one fidgeting.
Yeah. No, same.
I'm
same.
like, oh
Same.
yeah, me too.
I get
hate
distracted
that. Gosh.
so easy.
That's why sometimes I will be listening to something
Yeah.
while doing homework,
Well-
and I will and if I don't let my other parts of my body do something,
Yeah.
I feel like my brain will be like
Yeah.
everywhere because it wants
Yeah.
to do everything.
What kind of music do you listen to when you study? Do you listen to like lyrics or just?
Okay, song with lyrics. If it's too catchy, I can't.
Me neither. I was gonna say I can't do it.
But if it's like engaging conversations like what you guys are doing, or whenever I listen to a podcast, or I just listen to pure music.
Oh, see, I can't listen to a podcast. Oh my god.
Okay. When I so I listen
making me nervous over here.
No. I listen to a podcast
Yeah.
that's interesting that I already heard.
Ah.
So my brain sort of recaps what it is and thinks about
like
it
that.
while I'm doing my work.
Yeah.
So it can keep all the rest of my voices in my head focus on that while I can focus on my work.
Interesting.
You know what I'm saying?
Yeah, whenever I'm working doing homework, I have to have some music. And I think depending on the day,
Yes, depends on the day.
on
It depends on the mood.
the day and the time of day. Like as you know, my
energy.
your dopamine goes up and down throughout the day as well.
Cortisol levels and whatnot.
Yeah, but I listen to a lot of hip hop because I just like the energy of
The
energy
pop.
of it. Yeah, just it gives me the energy to get after it.
Yeah.
Or I'm either listening to that or there's this new thing that I've been doing is like listening to it's called on Spotify you can just search like study frequencies and it's just these like it's just these like apparently like frequencies that are good
I've seen
for
them, yeah.
focusing and things like that. So
I can't.
I'll
When
do
I
that.
listen to those, I'll get a headache.
Really?
Yeah.
Wow.
I do brown noise and rain.
Okay,
Brown
that's
noise.
fine.
I
That's
do
fine.
brown
When's your
noise.
study?
I'll
Yeah.
have one tab and it'll be
Yeah.
brown noise.
I think we're
and then
very
I'll have
similar.
another tab and it'll be raindrops. And I swear I can actually work longer. I think if I have that going.
Yes.
Like
Both of them?
both of them at the same. It'll be
Oh yeah.
Okay, is it
brown
like
noise and then
so it's like it drowns out the noise in your head, right? It's
Yeah.
like because I feel like we're similar in that sense is because if like for example if it's too catchy, my attention will go to the catchy song.
Yeah,
like with
yeah.
the lyrics, I would want to sing along.
Yeah, I'm with
But-
you there. Yeah.
Yeah. So, but whenever I play something that is more like it, sometimes it's like upbeat, sometimes it's more classical. Sometimes it depends on the mood and energy, so that it gets my attention, my like the background attention away,
Yeah.
while I can focus on my shit. Otherwise,
Yeah.
I will start chasing like my ideas. You know,
Yeah.
I'll start chasing, and I will not focus. Or I will start falling asleep. That's the problem with classes. It's the class they expect you to shut up and sit down.
Yeah.
That's the type of thing that will not allow me to like stay awake. So for example, engaging classes.
So you're
for
talking about math physics, bro? Is that
No,
a
no,
little
okay,
jab?
okay.
See,
so okay, here's the weird thing.
I have a totally different philosophy.
Yeah.
just
So
joking.
in math physics, for example, when he asks questions and I answer, that's engagement. I'll wake up. But there are days when he does not ask
Yeah.
questions at all. I will fall asleep.
Me too. I know.
See,
Back to
that's
the
why
board. Just
I'm always constantly
Yeah.
thinking of questions to ask because I think that's what keeps me engaged. I'm like,
No,
okay, well, how
I do
we
that too, but there are some teachers that don't be like, oh, do you have any questions? Some teachers just,
yeah.
See,
and
I-
that'll fuck me up.
That's a part of like what I was saying earlier about what my girlfriend said is like I am just to the point where no, you have to deal with me. Like I have to deal with you. You have to deal with me as well. So I'm gonna be myself, and even if it
Okay,
is
I
the
might start
professor,
trying
yeah.
doing that because, for example, I love Stapleton. He's one of my favorite professors, but
too.
he speaks so slow, so monotonously.
Yeah.
And he does every now and then be like, so you have any questions?
Yeah.
At that point, I'm already like nodding off, so I don't
Yeah.
have a question.
I see.
But so maybe next time I'll do what you do. So whenever he teaches and he has like a subtle pause there,
Yeah.
like when he's thinking,
Interrupt, bro.
that's when I will cut in. Because otherwise
yes.
I'll actually die in class.
I've had Stapleton. He is probably him and the Williams. I wrote. There was this thing that Lacey sent for
The Williams.
the Williams. Both of them. Have you had them?
No.
Either of them? No.
No.
Aaron or Ronnie Williams, Scott Williams.
No.
Oh man, yeah, that was Calc 1 and pre-cal. Yeah, pre-cal for Mrs. Williams, and then Calc 1 for Mr.
I did mine in Malaysia, so.
Oh yeah, I got you.
I did mine at Rose State.
Yeah, and then Stapleton for DE, and those 3 teachers. I said this in a little report the other day that Lacey sent out. It was like a prompt for us for like ABET, to like get some feedback on like what we think about what the student body thinks about you know our program here. And those 3 teachers in particular, I know Stapleton is hard to stay awake, and he can seem really drony, and not even seem, he kind of is sometimes.
It's a little monotony.
But I remember like I came into engineering really, honestly, I was so naive. I thought, the math portion, calc, differential equations, all these classes are going to be things that I kind of keep my nose to the grindstone on and just... I'll just get them out of the way. I'll do them, and then I'll be in the glory land, and I'll be able to, do the things that I want to do.
Yeah.
And it was really interesting. Those 3 teachers, I honestly feel like they made me, in a way, really come to love math.
Okay.
Like
Yes.
that is something I never thought I would be able to enjoy and sit down and do and look forward to maybe not every time, not certain things, triple integrals. I will never look forward to a triple integral, okay, or a lot of infinite series. The infinite series is kind of interesting.
Yeah.
But really, like I thought I was just gonna have to grind it out, bro, and be like, oh man, I'll just get it done and then I'll get my degree. And those 3, I feel like they really helped me. Just like fall in love with math almost. I love math now.
My favorite is Hendrik Lyons.
Dr. Lyons.
Lyons, I've heard she's good too.
Yeah.
She goes by Hendrix now.
Yeah. So, Dr. Hendrik Lyons, the way she's able to, I like the way she expresses math. She really is passionate about it, energetic. I know Stapleton is, and I think he's just past his prime. But I really think, I think he.
Sorry, David.
But he is. But but when I talk to Stapleton, like personally, you can tell he's a wealth of knowledge. I really learn a lot from him. The problem is. I think he just doesn't have. He's been doing this for like past 50 years or something. Yes. So he probably doesn't have the energy anymore. But
maybe it's just who he is.
Oh yeah,
I was going to say. I think it has to do more with what we're talking about: the communication, the checking in on, like, hey, and genuinely asking, are there any questions? Like, do you understand how this part relates to that part? You don't get that with him, and you do have to raise. Like, I remember I took DE over the summer, and
you already took DE.
Yeah, I took DE and Calc 4 over the summer, bro.
Oh my gosh.
It was a hard summer.
I bet it was.
But the great thing about doing DE over the summer is that I had the floor with Dr. Stapleton. Like, there was 4 of us in that class, bro, and I was the only one that was like Mr. Questions. Like everyone else. Well, the other 2 students were actually math students. I think they had to retake the course because they got a D in it. So they were kind of just there, like, I just got to get this out of the way. And then there was me and another engineer. And anyway, most of them were pretty quiet. And so it was nice. Like, I got to be able to really, like, actually not, like, impolitely, but straight up interrupt him. Because there's only 4 of us. Like, I'm more comfortable to be like, hey, wait a minute.
Why don't students do that, though?
I know. I don't get why they don't either. And just go to class every day, sit, listen, and it's like you're being whipped.
Yeah.
And then you just leave. I'm like...
If I don't understand something, I have to, like, say, hey, whoa, stop here.
Yeah, dude, well, hold up. And that's, you and Les, I remember, in chemistry, did that a lot. And that's, that I agree. I enjoy being around people like that.
I think the problem is... I guess for me, it's like culture. For me, at least back from where my college is, there are professors that are good. They always ask, do you have any questions? Yeah, that's when I'm comfortable asking questions. But when a professor does not ask that, they will be like, save the questions to the end of class type thing. And by the end of class, I'll forget the questions. I'll write it down, but I won't know, like, you get what I mean? The flow is not there anymore.
Yeah, no, Tej just Tej will be like, well, hold your question, let me finish this thought, and then we'll discuss.
Fine, because that's one thought. But some teachers, either they don't ask at all, or they'll tell you to save it to the end of class.
Yeah.
And that is when I get like, that's the lack of engagement is usually what gets to me.
I'm going to be totally honest here. I think that there are some professors.
Honest with us?
How dare you?
Yeah, you're just now getting to what I really think.
Yeah.
I do think that there are 2 types of professors only. There are only 2 types. There are professors that are meant to teach, that have a natural... don't get me wrong, like, teaching can be a skill. Like, you can build that skill. You can learn how to teach better, how to communicate better.
That's why there's education degrees.
I mean, sure, yeah, you can learn those things. However, I do think that there are some people that just have like a God-given, like it's just who you are, and you're good at it. And then there's other people I think that choose to be professors, and I think y'all know what I mean. Like there's some professors that are professors for their own sake, and then there's some professors that are professors for our sake, and for teaching sake,
didn't choose to but have to, maybe.
Right. You know,
because here's how the faculty, at least in the United States and in most of the world, works. If you're a professor or any researcher, you have to have a part-time teaching. You have to, because you're using their university facilities. So either you want to get paid to do research by a grant, or you teach and earn that position to do your research. That's the problem, because I can tell a lot of these professors want to do research. A lot of these professors want to teach, and you can tell they're very different.
Yes,
sure. I totally agree, bro. There are some people that they're here for the grants, and like, hey, I have my playroom and I get to do what I want, and that's cool too. You know, like, hey, that's your thing. But
and some people are just good at both,
and some are good at both. My dad was a professor. Not anymore actually. He went into industry, but that was a lot of my life growing up. He was a he is a cotton disease specialist. Ooh. So that was us being at Texas Tech and stuff.
Of course.
He was, their agriculture.
So much cotton in Texas.
Yeah, it's the cotton capital of the world, bro.
Yes, it's true.
Like it's great. Everywhere you go, there are cotton fields everywhere. And so he did a lot of that. I mean, grants from different companies, seed companies, chemical companies like Monsanto and Bayer and stuff. And so that was a lot of my childhood. Like, I know, bro.
Actually, later on, I have a few questions to ask you. But anyway, continue. But later on, I have important questions to ask you about. Later.
No, you're good. Yeah, but that was I got to see, like, growing up, a lot of the grunt work, that goes into research, because you're saying, like, a lot of teachers, it's like the holy grail is research, and that's what a lot of them want to really do rather than teach. Some of them, like you said, there's both, but like growing up, me and my brother, we had to do these things called stand counts, and so basically, working for my dad, we had to do these, and he would give my brother a clipboard, and he would give me a clicker, or the other way around, and he would drop us off at a field, and it was just a table of, like, each cotton field, say it's 10 acres, there would be certain, there's rows in them, and there was like 10-foot plots in each row, and say a group of 4 rows, 10 feet here, and then there's a gap, and then there's another plot, and they were all different types of seed. Like maybe each field was treated with like different, chemicals and stuff. And basically, like, this is like a big part of what we had to do is go up and down every row and count the number of plants in the field. Like, I had the clicker and I'd be like, 1, 2, 3, 4.
Oh my God.
And so imagine being dropped off at a ginormous field and just be like, count the number of total plants in this field. And so he would have the clipboard and I'd be like, okay, that row had 50. And so, it's really cool. Like,
people do that with the drone now, hopefully.
Yeah, right. No, I don't know, bro. Maybe.
I think they have auto counters now.
Yeah, I don't know. Man, am I that old? It's like, back in the day, we had to go out there with our handheld clickers. And with the clipboard is, drone boy. It makes me feel old. But to count, like, the germination, like, how many of them germinated. And then, like, it was cool. I learned, do you know, what's his name? Nash. In the math department, he's a math tutor there. Do you know Nash by chance?
Yes.
He has long hair.
I don't know him personally, but I know who you're talking about.
Yeah, we've had some really good conversation. You should bring him on here. Okay. He's a cool hang for sure.
Okay,
he's cool.
You'll have to introduce us. I haven't met him.
He's really an interesting guy. Yeah, he's a math major.
Okay.
And so we were talking, and like he was just saying like how it's really cool how other industries just start folding into one another, because like a big part of statistics, he said, was like in agriculture. Really like the majority of statisticians, like if you're going to school for statistics, like I guess like 80% of them actually work in agriculture for that kind of research. So I don't know. It's just cool, like talking to him.
Interesting. Yeah, going back to like what you're talking about with professors wanting to do research, right? Yeah. And it's sort of one of those things, like we have to always remember, like, professors are humans, and they have emotions and bad days and good days as well. Because I mean, it's interesting that professors can take like I forget what it's called, but where you essentially you don't teach at all, but you still get paid and you just go do your research.
Yes. But that's rarer.
That's at specific universities, I think.
Yeah.
This is UCO's a university where they if you're doing research right, you have to teach.
Well, Teo's sort of on. I forget what it's called, but
Because a pure researcher, I'm pretty sure it has a separate like department. You know, like for example, you're just a researcher and you're not a professor.
I think, yeah.
I'm pretty sure they have a separate like finance account for them.
I think it depends on the school. Like, whether or not like your school has that department of just research.
Well, Dr. Teo actually, so some semesters will teach less classes, and they do that to help him be able to do research, right? Like I believe this semester he's teaching less classes because he's trying to publish a paper.
Oh, okay.
Yeah.
But he has to fight for it, no? I'm pretty sure they have to fight for it. They have to be like, okay.
Sabbatical.
That's
what it's called.
Yeah, they have to ask for it though, right? They have to, okay, I'm doing my paper now. Can you please give me less classes type thing,
you
right?
probably have to do that. Anyway, I mean, but yeah. And so, I don't know. I've thought about. So I was having this talk with Dr. Benchbar the other day, and he said there's a need for American professors, well, and just professors in general, right? And where, especially if you're good at English, right? Because, sometimes, so the way that he was saying this is that, for instance, here in America, right, like a lot of our engineering professors are minorities, right? And
That's true.
But it's also good to have professors that sort of look like you, because then it's not in a weird way, but it just
be able to relate better, bond better, understand better, because you are from the same background.
Exactly. And sort of like a, I don't know, like, and just sort of like I can do this too, and so he was actually telling me that some professors get paid like extremely well, and I don't know, I've thought about like what would my life look like, because I really love doing research. It's one of my favorite things. Like I could do without the schoolwork and just do my research, right? Which I mean, I think
that's the dream.
Yeah,
that's the dream.
But then I think about trying to do research and then juggle, teaching classes and grading and doing all of that.
Life too.
Yeah, it's like maybe it would just be better to like. Get like only a research job instead of like being a professor and trying to do research.
That's why R&D is such a good job for researchers or like engineers.
Yeah, so I don't know, just something that I've been thinking about lately.
My dream pathway, at least for now, is I want to get into radiology, and while I'm in radiology, I can do research as a radiologist. Radiologists pay well. We are helping people because we're diagnosing them. Yeah. We have the technicalities with all the machines and whatnot, and we can do research. Yeah. And if they want me to teach while doing that, I honestly do not mind. I fucking love teaching. I love talking about science. Yeah. So, in my opinion, if I get all three, especially if they pay me to teach, why not? Yeah. My radiology pays well, research pays well, then teaching is triple the buck.
It's just perk. Yeah.
Yeah, it's just all perk.
Most definitely. Yeah. I really think we should get back to quantum mechanics.
Oh, yeah.
So I was thinking... Go ahead.
Oh, yeah. No, so basically I wanted to bring up something because what we touched on, right, just now in condensed and... Not condensed matter, solid state physics, all the relativistic stuff, it's called relativistic quantum mechanics. And I find that very interesting. For example, you remember how I talked about how some elements in the periodic table have electron shells that orbit so fast that they actually contribute to the mass. I found it. So it is berkelium and Einsteinium. In fact, what you'll be surprised to know is that the reason gold is because of something called 6s shell contraction, and that causes the electrons to orbit faster and the energy levels to change due to relativity.
Wait, I'm sorry. Say that again.
So So for example, gold, right? The color of gold, the reason why it's so unique in the periodic table is because the relativistic effects of the shells, because it has so many positive charge, right? The electrons go orbit closer, and when they orbit closer, they have to go faster because of angular momentum, right? So when they orbit so fast that their energy levels actually shift because they have different mass now and different energies now.
Interesting.
So that allows it to have the gold shiny look that we have. Otherwise, if you simulate without relativistic mass, right? Just simulate the gold without its relative, it'll just be silver.
Interesting.
So, and mercury.
So then silver and gold are like really close.
They're in the periodic table, they're right in the same family.
Interesting.
And that also explains why they're inert, because of how the binding energy caused by. But mercury is the other way. It's so reactive.
Yeah.
Because of the same effect, because of its relativistic electrons, right? They stabilize the atoms so well that the binding energy with other mercury atoms weakens because they're so stable.
So
they reduce cohesion.
is this? So I know there's the Planck-Einstein relation, right?
Yes.
So is this where they get those equations from? Like, is this where this relativistic quantum mechanics arises, or like, do you know?
So relativistic quantum mechanics just arise from the fact that you apply Einstein's and the Lorentz factor, right? E equals mc squared and the Lorentz factor and whatnot to chemical and physical systems.
Interesting.
So like, remember E equals mc squared? Time to get to the whiteboard.
Get it, dog.
Okay. So like, there is something. If you guys know the Lorentz factor, I believe it's gamma. It's square root of 1 minus v squared over c squared.
Yeah.
Right. So in the electrons when they orbit the atoms, right? So let's the relativistic mass. So let me just put this.
We may have to set up a mic over there.
Yeah. So I believe this is how it's supposed to be, but I might be remembering it wrong. But basically, the faster the electron is moving, or any particle is moving, the mass that they have actually increases. So for example, in like, let me just double check that real quick. So for example, in berkelium and einsteinium that I just talked about, right? The electrons in some of the inner shells are going 0.7 speed of light. So that means 70% the speed of light.
Wow.
70%. That's very fast. And the mass increase is 42%
Holy cow.
of the electrons itself, I mean. So they contribute to maybe like 10% more to the actual atom's mass.
Okay.
Which is a lot though. It's still a lot.
Yeah. I mean, yeah, the denominator, the closer V is to C, the closer the denominator is to 1. So, I mean...
Which makes it small.
Well, the closer it is to 1, the bigger it is. Like, as the denominator increases.
Because as the denominator decreases, because right now 1 minus something, right? So as V gets closer to C, the denominator gets lower, that more decimal points.
Oh, that,
Yeah. More decimal points, and when you
That's
divide,
what I was going with. Yeah.
So that's interesting. I don't know how. Don't you think it's just fascinating when you marry relativity? But this is special relativity. When you marry special relativity with quantum mechanics, you get.
Can you explain the difference between general and special relativity?
So general relativity is all about the gravity. So when you have the the Einstein stress energy tensor and all that crazy ass equation, that is general relativity. It talks about curvature of space-time, the gravitational waves.
I think of a bowling ball on a trampoline.
Yeah.
I think of that representation.
Yes, that's the good analog of it. But basically, that is general relativity. But that's the one that does not work well with quantum mechanics. When you put quantum mechanics equations into general relativity, things go haywire. Special relativity is the one that is already married very well with quantum mechanics. That's why you know QFT, quantum field theory, the best theory we have so far for quantum mechanics and particle physics, the standard model, right? That is special relativity. So we merge well, special relativity, we merge well with particle physics and quantum mechanics. General relativity does not.
But I'm having a hard time understanding what really the difference between.
Oh, sorry. I haven't explained what special relativity is. Yeah. So special relativity is more about reference frames for velocity, time dilation, but for motion.
Okay.
So gravity is not an equation. Special relativity, gravity is not an equation. So Einstein worked on special relativity. And then he realized, the time dilation, the mirror clock, and all that. So that's the Lorentz factor, right? If you apply the Lorentz factor, you multiply that to time. I believe you get the time dilation, the proper time, and that is special relativity. Using this and also the Galdinian idea of frames of reference, right? The frame equivalents like acceleration and velocity. So gravitational acceleration is the same as normal acceleration. He applied that to to gravity, right? And that's how he formulated general relativity. But it's just that the problem with that now is that the equations of general relativity, when you apply quantum mechanics to it, to the scale of quantum mechanics, things either gets too small or too big. So that's why they call it the chasm of ignorance, where general relativity and quantum mechanics just can't align.
Because the gravitational field between subatomic particles is so small.
And then when you go into black holes, it gets too big.
Right, yeah. Because, we just learned about that in modern... Have you taken modern physics yet?
No.
Oh, man, dude.
I don't need it,
I'm excited to see you. Honestly, you don't.
Everybody
you don't because
it.
No.
That's not what I meant. No, that's not.
I know.
What I mean is BME. I'm BME, so I don't know if I need it.
Oh, gotcha. That's what you meant.
No. That's.
I was like, obviously not, bro.
No. I don't want to. No. That's not what I mean.
I was like, okay,
I want to take the class. No. I want to take that class because that class is what as you can tell, I'm nerding over this because it's one of my favorite classes. Favorite topics. No, I want to take it, but I don't know if I need it in the sense of my
BME,
my flow chart. I don't think
you do.
Yeah.
I think it's just EP and electrical actually that need to take modern.
Yeah. That's why I kind of sad that if I'll ask Lacey if I need it, but I don't think I need it.
So the reason I take it anyway, bro.
You pay for my tuition, I will.
I mean, the reason I took it is because all I had to do was take modern physics, and I got a
physics minor.
Yeah, exactly.
Tempting. That's why I'm taking linear algebra. Because if I take linear algebra, I get a minor in math.
Yeah.
So I think I might do that. If I only need that to get my minor in physics, I'm just gonna take it. Why not? You get a free minor.
Yeah.
Nerd.
I loved the idea of the reference frames, bro. Like when we started learning about that blew my mind. Like, have you in our modern physics textbook, we had a thought experiment about a guy in a plane with a laser pointer.
Yeah.
Have you heard about that?
Oh, yeah.
Like that blew my mind because depending on where you are, the light traveled a different distance.
Yep.
You know, if you're on the Earth and you're looking at that plane and he goes click, click, it went in a triangle shape.
Yes.
But the dude in the plane sees it as up down.
Yes.
You know, and then like he related that to like
that's special relativity.
That's special relativity, right? Like if I'm in my truck and I take a tennis ball and I'm driving at 50 miles an hour and I throw it up and down, and you're sitting there next to me, it goes up and down. But if Josh is seeing us fly across the table in my truck, he's seeing it go like.
Yes.
So what distance did it go? What distance? I don't know. Where were you? You know, like, and it's so interesting to. I don't know. It just blew my mind, bro. That was seriously one of the few times that I've had in school where I was genuinely sitting there like, wow, this is getting cool. You know, it's no longer just math.
Okay, I also noticed one more trippy thing. Do you know how like quantum mechanics there's so many interpretations?
Yes, yeah.
Like
Good, yeah.
Gravity has the same thing. So you know how some people say gravity is a curvature? There's also an interpretation where gravity is a flow. So instead of thinking about yourself moving through space, think about gravity as space moving through you. Right now, there's a conveyor about like space is constantly moving down. That's why you're getting pulled down, accelerating down. So like imagine this, right? Back to the drawing board. Okay, so in that's 2 reference frame, you got little Albert here in space, yeah? And then this is just empty space. But and then you have Josh on Earth, right? On Earth. Now imagine instead of me moving down, it's space moving him down. You see the framing? So there's many different ways you can see gravity. That's why we don't know what gravity is, the same way we don't know what the wave function actually means. That's why wave function has so many equations, so many interpretations, right? The many worlds interpretation.
Yes.
Copenhagen.
Well,
the same way gravity has many interpretations. Some say it's just the curvature. Some say it's because of time. Do you know you can derive gravity just from proper time, but which is weird because proper time derived from gravity. But
well, and then aren't there interpretations of quantum mechanics that don't need gravity?
Sorry?
Aren't there interpretations of quantum mechanics that don't need gravity?
Quantum mechanics can't have gravity. That's the problem.
Okay,
yeah. So right now, if you apply gravity into quantum systems, it's negligible. They're tiny. They can't do anything.
I think I'm thinking of...
Because, okay, here's the best part. Here's my favorite part. Astrophysics, especially when you talk about stellar mass, that's when mass gets so big, so extreme that gravity starts affecting quantum systems. That is where gravity starts coming into play. But here's the issue, right? At that point, once gravity starts being felt at the quantum level, you start getting a lot of like numbers blowing up. So for example, so whenever people model the cores of stars, they don't use gravity. In a sense that they usually, I might be wrong, but they usually just model the system as just high pressure. They don't say where the pressure is coming from. They just consider it as a high pressure system. That's how they model the, when the stars collapse, it's just pressure. But they don't model it as, the gravity is causing the pressure. When you're simulating, right, you even when in simulations, you're just simulating as a force. Yeah. But they don't tell you what gravity is or isn't.
It's just a linear relationship.
Yeah,
right?
yeah. So that's the trippy thing. We still don't know what gravity is. The least, I won't say it's the least understood force, but it's one of the more mysterious ones.
What do you think is the least?
Weak force. The weak nuclear force. Do you know the weak nuclear force? It is particle physics. In nuclear physics and particle physics, weak nuclear force is what causes nuclear decay. If there's no weak nuclear force, the particles can't decay.
Okay, and nuclear decay is protons separating from neutrons. Right?
No.
Is that...
In this case, we're talking about neutrons beta decay. So neutrons, they turn into protons and they release an electron and an antineutrino.
Okay, yeah. I remember Teo talking about that actually, yeah.
Yeah.
Okay.
A neutrino or antineutrino. One of the two.
It's sort of one of the ways that they describe or models they use for quantum tunneling as well.
Yes.
So what is quantum tunneling? What is that? I've heard it. I don't know.
Do you want to give it a try?
Give me yeah.
Okay, I'll try it.
Write it down. Get to the board.
I'm good at that. Let's see here. I may need the board. I don't know. Let's see here. So, actually, you do kind of need the board, right?
You need to visualize
the
it.
board.
Okay, so, Okay, so in classical
physics,
right? So think of a big hill, right? But a hill that you could easily walk up, right?
Okay.
So in classical physics, there's some force that you have to apply in order to get up to the top of that hill, right? And then so in quantum mechanics, we sort of use this same idea to illustrate what's called a infinite well. And
Energy wells.
Yeah, infinite energy well. So if you think of an infinite energy, so okay, fuck it.
Draw it. Back to the drawing board.
Okay, so because we've learned this a lot in material or
Modern physics.
solid state devices
solid state.
and modern physics. So think of this and think of yeah. Okay, and so
I like the diagonal 8.
it's an infinity sign, man.
I draw mine as 2 separate ovals. I've never been able to do the infinity sign
This
ever.
is just to illustrate that it is infinitely tall, right?
Yes.
So there is, essentially it's saying that you have this particle that's in here, right? And it needs to go above this infinite well in order to get to the other side.
Okay.
Right?
Okay.
Well, in classical mechanics, you just walk up and you can apply certain force to get there. But in here, we're talking about an infinite well, whereas...
There's no way you can get there, basically.
Yeah, exactly. And so what quantum mechanics does is it says, okay, well, can this particle ever go through
That barrier.
Oh, yeah. Okay. I know where you're going
So
with
what
this.
it's saying is that there's the probability of this thing being able to go through this wall, and so
Is asymptotically but non-zero.
yes, so there is some probability that this particle can go through that infinite well, or essentially, I don't know if it's saying that it can have the same amount of energy, or it has the energy to go above an infinite well. It's just saying that there is a probability that it can just tunnel through that wall, essentially, that's there.
Because I've heard, like, I remember, what's his last name? Josh, Buff Josh.
Buff Josh.
Yeah.
He was telling me about that, and I think that has to do. He said one day he was talking about, like, you know, how, like, there is a probability for me to literally fall through this floor right now. Like, he was standing up and he was like, you know, there's a probability that I could just fall through the floor.
No.
And is that? I don't know.
No,
You know?
no, there's no way that
In classical mechanics.
I mean, I guess if you were trying to, if he's trying to say that he's a particle, he's a quantum particle, then yes.
Oh, okay.
But if he's saying I am me, then no, there's no like way you're gonna go through the.
I think because that is when you try to apply quantum to classical analogy, we call it. So you're using classical world like a wall, and you running towards the wall like Harry Potter trying to go to the like 9 3/4, right?
Yeah.
But this is where the analogy ends. So let me go to the drawing board.
Cool.
So this is my take on it.
Yeah, and if I butcher that, it's because like that's like my second time trying to explain that.
Okay, this is my take. Okay, my take. Take 2. So basically, if you've seen my lecture, me and Levi's lecture on pilot wave theory. So what we found.
Which the video is on YouTube for anybody who wants to go see it.
So in the quantum world, there is no physical solid wall. There's no such thing.
Okay.
If you think about it in a weird way, an atom, right, is mostly empty space, and then the fuzzy, like, where the electrons could be because it's orbiting, right? So the orbitals, it's mostly empty space. So if an electron wants to be in here or there, it could, because there's nothing actually stopping it. The only thing stopping it is an energy well, a well of potential. We call it a potential well. So now imagine, just now we talk about nuclear decay, right? So the nuclear decay, let's say we have a very big nucleus. Very big.
Yeah, this is a good way to.
Right? It has something called critical mass. Some of them is neutron, some of them is positive, some of them is not. So it has a critical mass where it has a chance of leaving. But because we have something Coulomb barrier. Coulomb is charge. Coulomb barrier basically states that to achieve fusion, right? When you want to marry two protons together, you have to go through that Coulomb barrier, that energy barrier, to get when the closer it is.
Okay.
You need to marry it, right? The only way you can get it together is to go through that Coulomb barrier, and it's a lot of energy. That's why only the sun can do it, right? Right now humans are failing at it. Same thing.
Okay.
For a fission reaction, the strong force is binding it together. Strong force is very strong. It's called a strong force for a reason. But people will be like, oh, the alpha decay, the helium nucleus, the alpha particle, has a small, minute chance of tunneling through the strong force. I don't believe that, because back in the day, they actually used something called the raindrop model. What they found is the nucleus can be modeled as a raindrop, and a raindrop, when it reaches a certain energy or size, it starts resonating. So it starts changing shape. And you remember how raindrops, when they reach a certain shape, or water droplet, when it gets too big, it just splits. They call it the raindrop model for a reason. So when a raindrop gets to a certain size, it splits.
It's a great analogy for the rainy day we're having.
Yes. So when just imagine the nucleus is actually wobbling like a raindrop. Okay. It has enough. Once it reaches a certain energy, it can just pop off. And in the quantum scale, everything is noise. Anything has energy. Any perturbation can affect it. So the noise gives it an extra boost of energy and probability to reach that fission state, to split off. So I don't believe that there's an actual the energy is actually, like, how do I say it? I don't believe that tunneling is some mystical probabilistic nature of reality. I believe it's deterministic. I'm on the determinism bandwagon.
Well, and so, let's see, how do I describe this? So in classical physics, right, you apply a force and there's a nice continuous curve to go with it, right?
Yep.
And in quantum mechanics, you don't have that beautiful curve anymore. It's sort of like a staircase. Yes.
It's a piecewise function.
Yes, exactly. And so using the Schrödinger equation plus quantum tunneling almost makes it feel like it is sort of helping make it continuous. In a way. Does that make sense?
So remember the double slit experiment thing that we showed at the pilot wave theory?
Yeah.
So remember that there's one section where we have the droplet bouncing around in a corral, and that corral is made from the same silver hydrophobic tape thing, right? So it will just circulate around here, right? But it has a non-zero chance of going through this shallow corral, and it can just go right through. And that's because that shallow corral is not a real barrier. It's just a slightly shallower part of the water. So it's not a solid physical barrier. But if that's a solid physical barrier, it's never going through. So what they found is the relationship between the possibility of this droplet going through the barrier has the same relationship as a quantum particle going through a force barrier, a force field. Basically, as the diameter of the little wall increases, the probability drops exponentially, just like in quantum tunneling. So just imagine, if you want to understand it better, don't understand it in the sense that we're throwing a ball at a wall and somehow the ball can just teleport through the wall. In the quantum scale, there is no wall. There is no ball. And if there is a ball, there's no wall for it to block it. It's just a force field. And there's always a chance for you to pass through that force field. You just need a strong enough force. And since it's not a solid wall, if you find the right angle, the right energy, you can just go right through. You just need the right energy to go right through.
Yeah.
And in the quantum scale, that's quantum foam. Quantum foam is like the quantum vacuum. The quantum vacuum is always bubbling with particles. Do you know about that? No. Okay, that's where. Okay, I guess we can segue into that. So you want to explain that?
Quantum foam?
Yeah, quantum foam.
I can't explain quantum foam, that's for sure.
So let me show you. I think we can put it as a link later for the people. And basically, the quantum foam, my personal idea of why sometimes a particle will have enough energy to go through a barrier is due to quantum foam. Basically, what they found is in the vacuum of space, empty space, you will have this. Oh. Why isn't it playing? You should be playing. So they found that empty space is not empty. It's always buzzing. Because quantum field is everywhere. So instead of thinking of an electron or... Okay, let's just take the EM field, for example. You know EM field? The electric and magnetic field, right? The space is everywhere. The vector space is everywhere. The vector is everywhere. It's just that everywhere is currently in classical physics is 0. That's why you don't sense anything. But on the quantum scale, all fields, all quantum fields, electric field, the magnetic field, every field is constantly randomly popping it like into random directions. Think of it as the Brownian motion of the quantum scale.
Okay.
So every now and then, in my opinion, okay, in my humble opinion, I feel like the reason tunneling comes from probability is because once you found the right trajectory towards a barrier, that quantum foam will nudge it ever so slightly to give it right enough boost to exit the barrier.
So are you saying that it could possibly be deterministic then?
I am on the quantum realism and determinism.
Yeah.
Bandwagon,
I mean,
if
so
you will.
this is one of the reasons that Einstein believed that quantum mechanics was incomplete, right? And it's because we have these probabilities, right? And he felt that the universe was deterministic.
God does not play dice.
Yes.
That's what he says.
And then another physicist of the day, his retort was, "Don't tell God what to do."
Yes.
Yeah.
It's true.
Yeah.
It's true.
And I think it was actually Niels Bohr.
I think it is, yeah.
Yes. Which, if you ever get a chance to read up on Niels Bohr, I
Brilliant
definitely
guy.
suggest looking at Niels Bohr.
Genius.
Yeah, and he was just really big.
Was he a chemist or was he a physicist?
No, he was a
Physicist.
physicist.
Okay.
And chemist, I guess. Applied physics.
Because I know the Bohr's model, like
Yes.
you know.
Yeah.
That I feel like that's the thing. If you read into history, most of the geniuses that make breakthroughs are polymaths. They dabble a bit in philosophy. They dabble a bit of chemistry. A bit of optics. You know.
Yeah. Well, you know, one of
Dabble here
our
and
favorite quotes is that innovation happens at the intersection of disciplines or fields. Right? Like for me, I don't think you can be a good engineer if you aren't, you know, if you don't
Well-versed
understand and well versed in a bunch of different
Fields.
Yeah.
fields. Right? And because a lot of the best technologies that we use today use properties of chemistry, physics, use all of them, not just one single one, right? So
Yeah, especially material science.
Oh, for
too.
sure.
Like, yeah, that is one that it just has everything. I feel like, I mean, pour into it, you know.
most definitely.
Yeah.
Most definitely. I'm sorry, I have to use the restroom so
Yeah, go
bad.
ahead, go ahead.
Yeah.
No, you're good.
So in the meantime, I'll explain how we know that quantum foam is real.
Okay, cool.
So the reason why we know that the vacuum has a non-zero energy
Okay.
is because there's something called the Casimir effect. And what they found in the Casimir effect is if you take two neutral plates and put it together, right? If you put it to a small enough distance, let's say like a nanometer or something, the plates will close together, even though there's no force.
So, can you go back to the
bubbling.
the bubbling?
This is talking about the bubbling. So basically, I'm just showing how we've discovered it.
Oh, okay. Okay.
So, at least how we proved it. So the bubbling part the quantum foam part, right? The reason why we call it quantum foam, it looks like foam. Is blah, 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 blah.
Yeah.
So it comes from Heisenberg's uncertainty principle. How you know how in a Heisenberg uncertainty principle you can know a position to so much before you have to sacrifice your knowledge of its momentum.
Okay.
Have you seen that?
I haven't.
So Heisenberg uncertainty principle. So most of the time, Heisenberg's uncertainty principle, people seen the position and momentum relation, right? But there's also another called energy and time relation. Basically, it says that you can you can only know so much about a particle's energy, but that sacrifices your knowledge of its state of how long it can be in that time.
Uncertainty principle?
Okay.
Yeah, uncertainty principle.
Let's go.
So I don't know if I can't explain it that well, but basically, based on this Heisenberg uncertainty principle, we found out that space itself, that quantum field, right? Because everything's a field. Right? So when you have an excitation in this field, that excitation in the electric field, right, is called an electron. You see what I mean? So in the quark field, when you have excitation, we call that a quark. But while there's no electron or quark, the field is still there and it's always buzzing. It can never be zero. That's called a vacuum state.
Like pure entropy.
It's just the field itself, just the pure field itself. It's hard. I don't know how to explain it, but
I promise I'm trying.
No. This is quantum field theory. This is where quantum mechanics marries particle physics. Okay. It's called quantum field theory. So let me just give you a better imagery of it.
So I found a really good explanation earlier. So I'll just read it off to you, right?
Yep.
So this is the uncertainty principle, right? To locate something tiny like an electron, we might use a very short wavelength photon, because short wavelengths light can resolve small details, right? So this is how we would measure, right? But a photon carries some momentum, a high frequency. A photon carries high momentum. So when this photon hits the electron to reveal its position, it imparts an unpredictable momentum kick to the electron, like a tiny cue ball hitting another ball. The more precise the position measurement, so the shorter wavelength photon, the larger the momentum disturbance. Thus, the act of measuring X precisely makes P, the momentum, uncertain, illustrating the uncertainty principle in a measurement context. And so it's sort of like, think about like a tennis ball, right? So for a macroscopic object like a tennis ball, photon's momentum transfer is negligible.
Because it's tiny.
Yeah, exactly. Yeah. But for an electron, a single photon can substantially alter its motion.
Yeah.
So instead of trying to imagine, so when we're observing a tennis ball, photons don't do shit to the tennis ball.
Right.
But in the quantum scale, trying to measure an electron with a photon is like trying to measure a tennis ball by shooting another tennis ball at it. What will happen is the tennis ball will ricochet.
Right.
And that tells us that and the same way a photon has momentum, right? Because it carries energy, right? So when a photon hits an electron, it'll ricochet, and the more energy, which is the shorter the wavelength, right? Because you want to be more precise. Shorter the wavelength. Shorter wavelengths, more energy means more momentum. When you hit an electron, it kicks it even crazier.
So the actual trying to measure where the electron is. In trying to measure it, we change its momentum. And so we can't get its position and momentum.
I see.
We can only get one or the other.
Yes, you cannot measure both at the same time. That's the uncertainty principle.
So can you explain, like you said, I mean, yes, higher frequency equals higher energy.
I'm glad that you asked.
How does that relate to the momentum of a photon?
I'm sorry, but so I've been thinking a lot about this lately, because me and Albert, we talk a lot now. And whenever you talk a lot, it's like there are just these things that you will eventually say that
sometimes makes no sense.
Well, no. Like what you just said, right? I'm glad you asked, right? Like it's just like whenever you talk so much, there's just these like things that are almost cliche, but it's just like at the same time, like
We're really glad that you asked.
What? Yeah. What? And then also, what better time to insert that? I don't know, just that statement, right?
Yeah.
That is very cliche, but also at the same time, like super fun.
So mind if I grab your attention to the classic E equals mc squared equation?
Okay, here we go.
So basically, everyone be like, oh, Einstein helped us find the energy mass relation, right? E equals mc squared. What people don't realize is the full equation is actually E squared equals to P squared times C squared plus M squared C to the power 4. And when you carry this term over,
then also it's actually a series, right?
yes, it's also a series.
Or Taylor series.
Yes and no. Okay, but first let's apply in the context of photons. Okay. So what happens when you apply in the context of photons? Photons, does it have mass? No. So we can do m equals 0, right?
It only doesn't have mass when a photon's at rest, though. Right?
Photons can't be at rest.
I mean, that's what I'm saying. Yeah. So they cease to be if they're like photons only exist when they're moving.
They can only exist in motion.
Right.
So now if you could put m is 0, what you'll get is p squared c squared, right? So square root of that is just pc. So p, as we can all remember, is momentum, and c. You'll be like, okay, your circular reasoning, you're just saying momentum is
That's basically it.
energy is momentum. Yes, no shit, we can, right? But what they found is, do you remember this equation?
Lambda nu?
And then, what?
Is it lambda nu? It's lambda.
Wait, frequency.
Lambda n?
Sorry.
I have it right here.
So,
E equals h nu.
Yes.
Lambda
E
equals h over p. Lambda equals h over p.
H over p, yes. H over p, but also
Lambda equals h over p. So
Lambda?
the wavelength equals h over p, and then we have it's related to.
So what I'm trying to remember is E equals to frequency. What's the frequency equation?
1 over t.
HF, right? It's HF, right?
Yeah.
Okay. Yeah.
So F is
1 over
lambda.
Is it 1 over lambda? 1 over
1
the
over period.
Yeah, which would be lambda, right? Which would be the
1 over period, and then 1 over period is lambda.
Frequency is 1 over period.
No, okay, I think we're kind of stuck. But basically, if you have this equation, right, you can derive your momentum into the photon's context.
Yeah.
So,
because it's hard for me because I see,
momentum.
The marker's right there.
Okay.
Yes, equals HF. E equals HF.
Well,
yes.
it's
so in a photon's context, the frequency is directly related to C over
lambda.
C over lambda, right? Yeah. So
Yeah, because the frequency is.
So now you can replace. So now you can, as you can see, you can you can equate these two. So you can do some algebra, and then you can relate its momentum to its. You can see equals PC. You can relate its momentum to its wavelength.
Okay, that's hard for me because I thought it was I don't know, maybe I'm still stuck in classical. P equals mv.
Yes.
And v is c, and the mass of a photon doesn't change.
Because the mass is 0, right? So momentum. In classical physics, if you apply this equation. Okay. Let's just do this. Okay. So let's just start from P equals mv, okay? Because P is momentum, mv. The problem with m is m has mass, they cannot have mass. So let's replace it with E, because E equals mc squared, right? So it's E over c squared, right? Now, the velocity is always at the speed of light because it's a photon, so it's c. What happens to c and c cancel?
Yeah.
So it goes to P equals to E over c. Now you get the same equation, E equals to P over c.
DC.
See? You get it back.
Yeah.
It'll all end up, always comes back to PC. Okay. See? So you can get it in two ways.
Yeah.
So one is, I think that's how Einstein derived his first equation. But basically, the original equation will lead you to E equals PC. If you derive it from HF, you also end up with PC. If you start with P equals mv, right? You will also end up with PC.
Yeah.
It all goes back to PC. So that's why in this context, that's how we calculate the momentum of a photon. And when you say momentum of the photon, how do we predict the energy and the momentum? You use this wavelength.
Yeah.
And the wavelength is quantized because of this h bar, thanks to Planck.
Yeah. Okay.
Yeah. So yes, they do not. Trust me. We it's intuitively it's hard to imagine momentum without mass. No one can. But imagine photons as pure momentum. Cause speaking of which, you know how P equals mv, right? P equals to mv. If you derive this momentum, if you integrate momentum with respect to velocity, you get 1 over 2 mv squared.
Yeah.
And that is kinetic energy. So that's kinetic energy. So whenever things have energy, so this is another proof. Whatever things has energy must have momentum, and photons have energy, so they have momentum. So if you think of photons as just pure energy carriers, right? Just energy carriers. We call them force carriers, but they're energy carriers. They carry energy and information. They also carry momentum. For physical particles like fermions, they are solid, so they have mass. And mass, also if you don't realize this, basically Einstein's just saying that mass is just confined energy. So if you have energy confined in a box, mirror box, and you just put photons in them, that box will have mass.
Yeah.
So that's just basically what it's saying.
That helps. I mean, that does help piece stuff together.
Yeah.
Really, because I had a hard time really understanding that. Like, E equals mc squared. Throw it on the board, and you can tell me energy and mass are related, but that does kind of make sense. I mean, if something has a mass, it has atoms, then it has energy as well. I mean, yeah.
But now the it gets even trippier is where does the energy come from, and that goes into even more trippier topics. But it gets a bit wishy-washy and hand-wavy. One is because we are not experts on it. Two is also because I feel like if we have a professor here, they can probably derive the whole thing from scratch. I think that would be even more clear.
Yeah.
But this goes into the ontology of it, right? What is an energy? What is momentum? We don't know.
Yeah. Well, I'm glad that no one else knows because this modern physics course has me second guessing everything I thought I knew. I got to this course and I seriously started asking myself well, what is energy then if it's now everything? It just seems like everything.
Yeah, I think that's the thing.
It's energy now.
Yes, it's sort of trippy about temperature, right? Is that temperature is not really a thing. It's something that we derive because of the movement of electrons or movement of particles in space.
Vibrations.
And the warmer, the hotter it is. So as you raise the temperature, the more jiggly things get.
So it's okay. No, I saw this meme. Okay, I think it's just perfect. If you think about it, temperature is just a speedometer on every particle, and you average it out.
That's actually really cool. Yeah.
You just
it's a speedometer.
It's the speedometer of particles, but you average it out.
Wow. That's interesting. I've never heard that. Yeah, that's cool.
It's a meme. I saw this as a nerd meme, but
So, Albert, can you sort of tell like why is there different interpretations?
Because we don't know what it is. For example, what is a table? I think it's okay. This goes back into, I feel like philosophy, there's a beauty of philosophy, is that it makes us realize where all this vagueness come from. One, the vagueness of language. Two, our perspective on stuff can be vague. So one is language. So when I ask you what's a table, can you define what's a table? Or what's a chair?
This is interesting because the thing that comes in my head is I think of things inside of my head. I think of these objects in my head, right? And I have an image of them, but if I were to describe them, I would describe them in a way that sort of anthropomorphizes them.
Or you will be missing the point, right? For example, when you say a chair is what you can sit on. You can sit on a table, doesn't make it a chair.
Yeah.
You see what I mean? That's the vagueness of definitions of language. Language comes with context. Context comes with function. That is the issue with ontology, is that when you try to ask what is something, you must first describe what it isn't. So that's the beauty of natural philosophy, which is science. It's also negative philosophy. Basically, what we do is we remove what isn't first. Process of elimination. It's always better to talk about what something isn't than what it is. So it's like what? It's like what Dr. Prather says. We get asymptotically close to truth when we use what was his little matrix thing?
It's geometric inference or not geometric inference. Yes. It's I can pull it up right now.
Yeah. So basically, me and him and Dr. Prather, we actually talked about this. But basically, when you ask quality questions, you will start going. You will start getting closer to truth of what something is or isn't, but asymptotically close. You can't get to it.
Right.
You will always miss it.
Yeah, and I think that's sort of what's sort of the most fascinating thing to me about really just life and in trying to apply the scientific method is you find out that there's these things that you can't probe for. Right? Like you can't probe for when the beginning of time was.
You can infer, but you cannot probe.
Yeah.
And I think that's the beauty of it. We can probe a table. I can see the table. Sorry for blind people, but I can see the table. Right? I guess but then we base it back on the definition. We define this as a table because of its function. So you see the problem here? It's like sort of like circular reasoning. You cannot go further than that. You just define it because of its function. So same with the electron. We say an electron is what's carrying a negative charge. What's next? You get what I mean?
Yeah.
Does it have a structure? We cannot probe anything further, so we cannot define it anything further. And since we are left with this black box, interpretation starts sparking.
And you're able to like do more observing of how these things interact with the world. Like instead of, like you said, that's really the end of it. It is something that carries a certain amount of negative charge. And what I like, we were able to see how it reacts to different environments, different voltages. What happens when we, and that's where I feel like you get to come in and start kind of just poking around and probing it. You get to start doing your own thing to really like learn more about how it behaves. Like the behavior.
So that's also why how electrons move from negative to positive, but current goes from positive to negative. That's because I think I told you and Anjali before the history of how electricity was discovered. And then they define it as current goes from positive to negative. And then we discovered these things called electrons that cause the current to happen. But we realized the electrons go from negative to positive, and we're like, oh shit, we don't know what to do.
Thanks, Benjamin.
That's why, that's why we label them as negative electrons. But electrons are the one that's carrying the current.
Yeah.
So you see, all the things we ask the problem is too vague. Every definition is technically circular. you will always hit a wall. A definition cannot define itself. It's circular. That's also Gödel's incompleteness theorem, right? Math cannot, at least arithmetic has a limit. You cannot derive arithmetic from its axioms. You will hit a wall. It's incomplete. Math is incomplete. And then you have undecidability and incomputability. Incomputability just means that a simple example is a program cannot predict whether its own output. Halting problem. Alan Turing's halting problem.
So I got a question for you, Jack. So I think we hit on most of the question, maybe even all the questions. I'm not really sure. Do you? Is there a question that we've left out? I feel like there maybe is something.
I mean, honestly, I did have one question that I wanted to talk about just this graph, right? And I start looking at this, and I really I want to, I guess, understand like the axes of y and z and x, right, of this graph here. And I think like my first interpretation is, okay, x represents the direction in which a photon is traveling. Because Dr. Teo told us that photons, though they can be emitted by a star or a light in all directions at once, like it can only travel in one direction. It's linear, and it doesn't just up and change direction. If a photon's going this way, it'll continue going that way until it hits something. And so that I kind of understand, but I want to understand, I guess, how and I don't know if this is really me asking you to explain Maxwell's equations. It probably is, like, explain Maxwell's equations.
Yeah.
But how does a magnetic field and the electric field, like, I understand amplitude, right? Like the strength of the wave, that's the amplitude. But how is it that they're oscillating, like, we start at the beginning, right, at the origin, and magnetic field is positive, 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 and now it somehow reaches a negative value. And the same thing with the electric field. Like my understanding is, like, in electrical science, we have like alternating current is represented as a sine wave, and based on frequency and things like that, I mean, it is oscillating. Okay, voltage is positive, 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 and then it passes the x-axis and it becomes negative. And so electrons now move the other way for a very, like, almost infinitesimally small period of time. They're just vibrating back and forth. Like that, I understand, like, in electrical science, that made total sense. I was like, okay, cool. You know, they're sitting there vibrating, going back and forth, back and forth. It's alternating current because the voltage source is a sine wave. So what is it about an electromagnetic wave that gives it those same properties, that goes positive, negative, positive, negative? Does the magnetic field, is it like, it's just hard for me to understand.
So
like,
whenever you think about that, right, remember it's a vector field. And what that means is that pointing, that up and down, it's not magnitude. It's not saying that's a negative of something. It's a direction.
Okay.
And also another thing is a similar fashion where when you have a rope, right? When you do a rope, the wave traveling through the rope is not, the rope itself is not traveling. So here's the craziest, trippiest part of it, right? The photon itself is not the field traveling. The arrows are not traveling. The arrows are like the rope. They are a series of vector values that carries the electric and magnetic field information forward. So they rise, and so look at my finger. They rise, fall, and rise, and they create a wave similar to the rope. But the field itself does not move. Nothing is actually moving. The wave is. So that's what an EM wave is. Now you'd be like, okay, so what is the EM wave? Is good. Now we're getting to the right part. The electric field and the magnetic field, right? So when you have an electron, right? When you have a charge, you create an electric field. Photons or any EM wave or any EM radiation only comes from the change in electric field. So when an electron's accelerating, you create electric, there will be EM field or EM wave. When an electron's decelerating, there's a It releases radiation. Now, here's the interesting part. When an electron's moving forward, now you suddenly turn it. It's changing vectors, right? When it's changing its direction, it releases also a so imagine it like water, right? Water is not doing anything. It's the change in motion of the water that creates the wave. So when let's say you put a rubber ducky on the water, you move the duck forward, it creates the wave forward.
Sure.
When the duck is slowing down, it leaves behind waves as well. But if it's a constantly moving duck in a what's it called? In a river, right? It sits with the river, right? There's no waves. But when you try to stop the duck while the river is moving, it creates waves. So it's the relative motion of a charge in the field that creates the magnetic field. So I guess the best way to show is an animation, I think.
Can I? I'm gonna run to the restroom real quick.
Yeah, go ahead.
So have you seen Three Blue, One Brown?
Uh-oh.
Yeah. So have you watched Three Blue, One Brown?
Which video?
He's illustrating the electromagnetic field.
Let's see. I can probably look it up right here.
Yeah. Origins of light is called it. How wiggling charges give rise to light.
Let's see here.
So you guys should
what is it called?
How wiggling charges give rise to light. I definitely recommend everyone to watch it. Remember, those directions, those vectors, are not actually anything traveling.
General outline for an explanation.
In the last video, you and I looked at this demo here, where we shine linearly
Can you
polarized
pull
light
it up
I'll
there?
pull
in
it
a tube full of sugar water. And
That's me. My bad.
Let's see here.
Yeah, we can. Once he comes in, we can show it there.
Polarization direction of light.
So we have.
Can you make it louder?
Yeah.
Shine linearly polarized light through a tube full of sugar water, and we saw how it rather mysteriously results in these colored diagonal stripes.
Oh yeah, that's even trippier. It's
Outline for an explanation.
it's called
Keeping track of what light still needs.
circularly polarized light.
Why does sugar water twist the polarization direction of light? Why does that twisting rate depend on the color of the light? And why, even if you understand that this twist is happening, would you see any evidence of it when viewing the tube from the side with no additional polarizing filters? Here, I'd like to begin with the very fundamental idea of what light is and show how the answer to these questions can emerge from an extremely minimal set of assumptions.
Right? So photons come from a change in charge or change in the electric field. It's a perturbation.
Yeah.
A constantly moving electron in one direction does not create changes in the electric field.
Yeah. So Three Blue, One Brown is great. I was watching a video of like the Fourier transform and the the Fourier and the Laplace transform.
Oh, yeah.
Which, if you're in signals and systems, like that,
You have to learn that.
Yeah.
Oh my God, Laplacian transform and all that. Oh my God.
Oh yeah, didn't you just take a differential equations test?
We will, but no, we will be learning this.
Oh, okay.
It's, I think it's one of the final chapters.
It's not that bad.
It's not that bad. But I mean, we learned the Laplacian in mathematical physics.
But you're gonna use Laplacian in signals and systems, digital signal processing.
Because it
you're gonna learn control systems.
yeah, it's the partial derivative.
Anytime you have derivatives in a differentially, which any system it can be mapped with differential equations. So you're gonna have.
I have to learn the differential equations. Yes.
Yeah. But
No, my problem is I get confused with what the differential equations methods are looking for. I know they all are trying to find the lowest derivative, you know, because we start with differential equations. We're trying to find the original equation, the characteristic equation. But then when it asks us the Wronskian, for example, I don't know what they're looking for. And then I read into it, then I realize it's whether something is independent or dependent. You see what I mean? I just need to know what we're looking for, and it intuitively clicks. You just need to tell me what we're looking for. If you don't tell me what we're looking for, you show me this equation.
yeah, no, they just say, hey, here's the math.
Here's the math, and he uses the
Here's how
technical
you
jargon.
solve it, yeah.
He assumes that which we're supposed to know the technical jargon, but sometimes we just don't. and that sort of confuses me.
Yeah, I think sometimes it's better to know the overall picture, the big overview of a topic or of of why you're doing this equation first before you start diving into the equation, right?
And that's the why and how.
You want to see the application of it so that you can see this is
what is it describing? Because math is a language.
Yeah, it's sort of giving the reason why I'm learning this freaking thing.
That is how my brain works.
Yes.
If you start throwing crap up on a board, bro, I'm probably gonna eye roll you.
Like right there, right?
Yeah.
It's hard.
Which is kind of hard to do this during a podcast because I think most people are going to just check out real quick.
Yeah.
But
I get it. I mean, I don't know. It's just I feel like there are certain times in classes where professors do need to do that. There's not much
because they have to assume you know. Otherwise, why are you in his class? You should know the basics.
That's true. And there are some times where they assume that you are on the same page. Hey, maybe you're not. Ask a question or get up to speed after class or whatever. And then, I don't know. I feel like there are other times, though, where it's like, hey, you just, like, there's other times where Teo has thrown up equations on the board, and the answer to the question that I have in my head actually ends up just being revealed when he's done. So it takes that, like, sense of me being like, okay, I need to be more, like, just receptive, pick up what I can, and, not be so, like, well, why? Like, starting off, like, I tried to do that with differential equations, and seriously, I had, like, not a full-on breakdown or anything, but I remember 2 weeks into that class, I was sitting in the library looking at a DE, and I was just like, dude, what even is a derivative? Like, I have suddenly now, like, this makes no sense to me. I had to go back to Calc 1 and PSE 1 and acceleration and velocity and, like, the limit definition, and I remember I had a conversation with Cole Rank. And he, I was telling him, like, I'm kind of frustrated that this is like a class where I really just cannot, like, understand anything. Everything up until that point had been sort of, like, I could pick up what we're doing and why it was like.
And suddenly a slap in the face.
Oh, dude, DE is just like, sit there, shut up, and do math, and you'll figure it out later. Which is, it's hard to,
Yeah, that's why I after. Oh, sorry.
No, go ahead.
That's why I find 3 Blue 1 Brown so helpful because he has a series called Differential Equations, and he explains what an ODE is, what a PDE is, and
I need to watch it.
You need, and it's the same channel.
It's such an intuitive look into just.
He visualizes
what it all is, like what
Yes.
these equations actually do, and visualizing the things that you're working with. Yeah, and so it's interesting because you have to have, as a student, you have to have a sort of balance, right? You can't just try and understand everything, right? You can't sit there and ask the why infinitely, right? You have to at some point shut up and calculate, right?
Yeah. Yes.
And I mean, for better or for worse, I don't know, but at the end of the day, you have a test you have to take, and you have a degree you want, and so if you don't put in that work, well, you could end up being in school for 10 years.
It's true.
So I always tell students who maybe, I don't know, struggling and are too focused on the why.
Yeah.
I just say, hey, dude, you've got a test coming up. You need to figure this out.
Exactly.
Like, just figure out just do the repetition of solving the problems.
Then ask it later.
Yeah, exactly. That's
or
why
you can
there's
ask
breaks,
along the way.
right?
Or you can ask along the way.
Research.
Yeah.
Get into research, because then you're going to be applying a lot of these different things, right?
Yeah.
And then you may even get paid to look deeper into the why, right? So don't do it for free. Go and get paid for it, and go do some research. But I don't know. I think we need to start wrapping this thing up. It's 2:55. We're 2 hours and 47 minutes in.
Yep. I think we should show him this first?
I have to go.
You have to go?
Yeah,
That's all right.
yeah.
Okay, I can show you later.
Yeah, show me later, bro. Because
Yeah.
I love 3 blue, 1 brown. Like,
So
that
helpful.
help. You want to talk about like the way that I can't get past things if I don't understand. He really is the dude to go to, and I'm surprised I didn't think of that. Looking him up for DEs and stuff, because I guess I thought he was the linear algebra guy, and it was just linear algebra, and that was kind of
Yeah, that's true.
No,
But
there's a lot of like, even if you just put in problems that you have, like actual homework problems into YouTube, a lot of times they'll pull up and there's somebody explaining them. Yeah,
Just random guys solving it.
Oh, I thought you were gonna say him. Him explaining it. Oh, yeah,
no,
no, yes, I agree. Yeah, I've done that. Yeah, there's actually a lot of textbook problems that people.
Yeah,
I don't know if they're
Solve
just
online.
super famous
YouTube is
problems, but
a great resource.
I am a YouTube university student for sure, bro.
Yeah.
I am on YouTube all the time.
Yes.
helps.
But anyways, I don't know. I think this is a good place to wrap it up.
Yeah.
Dude, thank you for doing this. I'm so
Bro.
pumped that you agreed to do this.
Of course.
I think some people can be a little timid because they think that we're going to force them to be an expert on a topic. But as you can see, a lot of times we don't even know what we're talking about, and we're just curious minds looking for other curious minds, and trying to put our curious minds together to figure out what the heck the universe is trying to tell us.
Yeah, bro. I know. I'm very thankful that I got to come. It was fun, bro. I had a good time, and it's given me some more stuff to put in my pocket to chew on. You know, for later on.
And you know, down the road, you know. You're welcome to come on again for sure. You know, if you have like another topic you want to dive into, you want to start like doing some research on a certain topic, and I think this would give you a good reason to do it, right?
Yeah.
That's why I like research, right? Because I'm just like, it gives me a reason to dive deeper in that thing.
Oh yeah.
And this podcast, right? We've learned so much by doing this, man. You know, we've gone over so many different topics: information theory.
On like what's it called?
Cosmology,
epistemology.
We're going to be getting Dr. Waters on, which she is a chemist.
Yeah.
And her research is in drug discovery, which is going to be really interesting. She's done research in cancer at the National Cancer Institute.
And someday we'll hopefully get Teo.
Yes, yeah. So
that would be fun, bro. That would be so awesome.
So yeah, dude. Thanks for doing this.
Absolutely.
Thanks
Thank
for
you guys.
Thanks for having the.
I don't know. I'm just glad that you are here to share your passion. On drive to learn. You know, it's just refreshing to finally see another student.
It is
here.
refreshing. Fills up your cup a little bit.
Yeah. Because every time it's just either us or a professor. Yeah. And finally we have another student.
And hopefully we have a few more students coming on. Josh Thompson and Orion. Going to be talking about the physics of music.
Oh wow.
And the physics of like how energy gets to your house, which to me is like kind of interesting.
Electrical
What I want to do, bro.
Yeah,
that is eventually what I want to go into is transmission, distribution, generation. How does this happen? How are we doing? Like it is like that's honestly something I'm really passionate and I would love to I'll be listening to that one for sure because that is like that's hitting all the right notes, bro. It's so cool.
Thank you for being courageous. Thank you for coming.
Of course.
We appreciate you. We end every episode with a clap like we started. So but first,
until next time.
Until next time. 1, 2, 3.
Oh, wait, do it again.
1, 2, 3.
No.
Hold on. Albert counts down.
Okay.
You count down.
I'm dead.
On 3. We clap on 3.
Oh, on 3?
Yeah.
Okay.
1, 2, 3. Yes.
All right, there we go.
Okay. Sorry, Brody.